Okay, so first I'd like to thank the organizers for inviting me to speak in this beautiful place. So this is work done with Youngju Baek, who was a postdoc at the Technion and is now at Cambridge, Alex Solon, who's moving from MIT to Paris as we speak, Xingpen Xu, who's, you probably don't know this institute, it's the Guangdong Technion Israel Institute of Technology. Guangdong is in China. So. And Nikolai was a student at the Technion, and there's also a result that I'll mention, which is an extension of these results to the interacting case that was done with a student at the Technion, Omer Granek, and are unpublished yet. Okay, so I want to first put this in the context of other talks that we've heard today, so in the last week. So there's been lots of discussion of diffusion of objects inside cells. And one of the things that we neglect when we do these simple treatments of bodies inside cells is the fact that there are really hydrodynamic interactions that are between many objects in the cell, and that makes the problem really more complicated. But also, that's why people neglect it, actually. But then, in many experiments, hydrodynamic interactions are not so important because cells, for example, are held next to a surface, and then the hydrodynamic interactions are screened, and you don't have to worry about that. What I want to argue is that if you put two objects inside a cell, the fact that the cell is a non-equilibrium system which contains active particles immediately implies that the bodies. Yeah. Okay. Okay. Immediately implies that two objects inside have long-range power law interactions between them. And what I want to do is to argue why you have these interactions. The argument is very, very simple, and then show you how we quantify them for a particularly simple model of active systems. Okay, so since I'm not going to assume that anybody knows what active systems are, just a really very quick introduction to them. So these are non-equilibrium systems, where each particle on its own consumes energy and dissipates it, and the result of that is generating motion. So they're intrinsically out of equilibrium. And the classic examples, again, I'm doing it very, very quickly because I assume that you've heard it. The classical examples are a sea of bacteria. So this is a classical movie from the Howard Berg lab that's shown probably thousands of times. And you see E. coli bacteria. And if you follow the E. coli bacteria, they have funny trajectory. It's roughly two kinds of motion. One where the bacteria moves in a straight line. That's called a run. And then about once every second, it stops and performs a tumble where the bacteria, to first approximation, chooses a new random direction and starts moving in that direction.
What is the medium?
The medium, this is water here. Okay, but okay, these experiments have been done in. Another example of an active system, this is an artificial system, and now there's a whole industry of producing these artificial systems are self-propelled colloids. So there's tons of work on these things. And this is from the Dave Pine group. And what you see here are colloids which are asymmetrically covered. And they're put into hydrogen peroxide, which is H2O2. And when you shine UV light on these colloids, there's a chemical reaction occurring at one end of the colloid, which propels these colloids in a specific direction. So this is the movie. This is with light off. You can see just normal Brownian motion of these guys. And then you turn the light on, and they start being self-propelled in this particular direction. And then the direction, of course, performs some random rotational diffusion, which reorients these particles. So the words that people call this is active Brownian particles. And there's tons of other active systems which are studied very carefully today. For example, shaken granular systems, which are particularly clean realizations of active matter when you can look at many things, molecular motors, actin polymers, and you could make a very, very long list of these things. Okay, so back to my talk, and the premise of the talk is very, very simple. You take an active fluid of particles, and you place some object inside this fluid. And I've chosen an object that's not symmetric. In particular, it's not spherical symmetric. And we know that if we take something that breaks time reversal symmetry and we put something asymmetric inside, then it shouts that the system is out of equilibrium and generates current. Okay, that's ratchet current. We know that for a very, very long time. And you know that if you generate the current, you're pushing on the particles, so that also means that the particles are exerting a force on you. Okay, that's just simple physics. And this has actually been observed in countless experiments. For active matter, this is the first movie I'll show you is from Roberto Di Leonardo, where they just put an asymmetric ratchet potential inside a sea of bacteria. And you can see that these are being pushed by the bacteria, sort of a small motor driven by bacteria. You could, there are experiments which are more similar to what I've shown here. Okay, it's a bit hard to see, but there's a wedge here that's placed in a sea of bacteria, and you can see that they're being pushed. So when it's rotating, it's actually an external magnetic field, but you can see that it's being pushed because of the forces exerted on these objects. Okay, so again, breaking of time reversal symmetry immediately implies that you have a current and a force on the body. So the idea is very, very simple. I take two objects inside an active media, and each of them generate a current. Okay, and each of them generate a current, and the current is related to the force acting on each of these bodies. And the idea is that if we have two objects inside this medium, then each of the objects will modify the currents in the region of the other object, actually density also. Yes? Yeah, of the active particles. Okay, so you're placing some objects inside the active medium, and the active medium starts to flow. So it's, okay? Okay, good. So each of these objects is modifying the neighborhood of the other object, and that will generate some long-range interactions between these objects. And what I want to do is to show and quantify these interactions for a particularly simple model of active matter. And I'll show you first that they're long-range, decaying as a power law. There's two interesting components. In 2 dimensions, they decay as 1 over r and 1 over r squared. I'll discuss them, and you can easily generalize everything to higher dimensions. I won't discuss. I'll talk for simplicity in 2 dimensions in the talk. That's also the one relevant to experiments, many experiments. The other thing is that these interactions, okay, they're generated by currents, so you can all guess immediately that they're anisotropic, and we'll see that explicitly. And the final interesting thing is that they don't obey an action-reaction principle. So you can have some funny situations where one object is not exerting a force on the other guy, but the other guy is exerting a force on the object itself, which is very different than, for example, hydrodynamic interactions. Now, I want to stress that these interactions occur also in dilute systems. So you could do the calculation with 0 interactions between the active particles, but it's still there. Now, typically, you're slightly embarrassed when you do non-interacting work. Okay, we should put some interaction in our work. But I'm stressing it here because these interactions are really in your face. They're really hard to avoid, and they're not a result of something subtle inside the medium, as opposed to, for example, Casimir forces, where you have to fine-tune things and have interactions in the media. These are very hard to avoid. Now, technically, if I forget to say it, what I'm going to do is characterize these interactions in terms of single body quantities. So you put a single object inside an active fluid, you measure properties of the single object in the fluid, and then you put 2 objects inside, then you know automatically the interactions between them. So that's what I'm going to do, and I'm going to do it in what we call a adiabatic limit. Namely, the objects are static inside the medium. What happens when they're not static is interesting. We're not there yet. Okay, and the results, all of the results I'll show you hold both for non-interacting, and we can show that they're exactly the same, actually, when you have pairwise symmetric interactions between the particles. Nothing has changed. Yes?
Static, but can they change their waves?
No, they're just static, but I'll show you movies where we can, using these things, infer interesting things. But no, we're not doing the motion. Okay, so one of the nice things that comes out of this calculation is that you can show that you can, to a large extent, control the interactions by controlling the shape of the objects. So if you do smart things, you can actually generate some interesting, I don't know, you call it self-organization or whatever you want. So this is one example. These are two pinned semicircles. So this is one semicircle who's pinned to the surface and has to rotate about the center of the circle. And this semicircle is pinned at the apex. And if I just had, I'm not going to show the movie, if I just had one object inside this active media, which you don't see, it's in the background, I'm not showing the active media, then each of these guys would just perform random rotational diffusion. So nothing spectacular happens, but once you have put these two objects inside the media and you fine-tune the properties, this doesn't happen generically. And if I have time at the end, I'll show you why this doesn't happen generically. But if you do that, then you can actually cause them to rotate together inside the medium. The direction is, of course, random. So if we wait long enough, then okay, they start rotating in the other direction. Okay, so again, you have to fine-tune things to achieve this behavior. This is another example, and again, it's fine-tuned. These are the same two objects, different parameters actually, and now they're allowed to move inside the medium. Okay, so our theory doesn't cover it because they're moving, but we can actually explain this behavior. Here we can give a quantitative theory, actually. And so now they're free to move, so there's a force pushing these guys in this direction. And initially what you'll see is that they start moving in the direction that each of the force the active medium exerts in each of them gives them. So they're just moving about. So it's initially boring, but now they hit each other, and they form this bound pair where one is chasing the other. Okay, so if you, again, if you fine-tune things, you can actually control what things do inside this active medium. And if I have time, I'll get to explaining the physics of this. Yes?
Just a very general question. Once I had a talk about hydrodynamic interaction, they said that if you have two bonds in water, they will attract each other, that's why bonds don't collide. That's not active transport.
No.
There is attraction.
No, this is...
So what is the difference? Why do you need at all these shapes?
Well, we'll get to it. Okay, so these behaviors require no action-reaction, first of all, okay, which is not the case in hydrodynamic interaction. These interactions also, just to make it clear, they occur even if the objects are static. Okay, because it's sort of inverse hydrodynamic interactions. They're generating a flow.
If you have a flow in hydrodynamics and two static bodies, they will not.
If you have a flow and you have two static bodies, you will have interactions. Okay, but here there's no. You hold the objects, they generate the currents, and that leads to interaction. And the interactions are different than hydrodynamic interactions.
The total net current is zero?
The total net, no, you generate currents, but they're not external. It's generated by the system itself, in contrast to the setting that you're discussing. Okay, and also they're different in character, the interactions. And we want to quantify this. Okay, so the outline of the talk is follows. I'll introduce the models that we use, and they're very simple, and many people here have looked at these models also. They're active Brownian particles and run and tumble particles. Then I'll discuss a single object inside an active fluid and discuss the behavior of the density and current field for a single object. And once we understand that, it will be very easy to understand the two-body interaction. And everything I'm showing you, we can do very cleanly and rigorously. And I'm giving you just simple arguments. Okay, if I have time, I'll just sketch how you do things rigorously. I'll do a small diversion in the middle, and if I have time, I'll actually go back to the movies I've showed you and explain the behavior that we saw using these interactions. And then I'll have a summary and outlook. So a quick recall for those of you, or introduction for those of you who don't know these models. Active Brownian motions and run and tumble particles. So these are particles which have an arrow on them. And the arrow is pointing the direction of motion. So the equation of motion is that the particle has a velocity induced by the activity. Okay, so the fact that it's driven by a force, there's actually force acting on it, is the fact that it's out of equilibrium. That's the drive. And the equations of motion are very, very simple. It's just a motion in the direction of the arrow. And you can add diffusion of the center of mass. It doesn't change anything. Okay, and then the two classes of models are run and tumble particles, where at rate alpha, the particle stops, chooses a new direction, and starts moving in a new direction. Or active Brownian particles, where the angle just performs a rotational diffusion. So if you want to go back to the movies, run and tumble are the E. coli bacteria from the Berg lab, and active Brownian particles are the Pine lab example. So these are movies of the two models. So this is active Brownian particles. And on large length scales, it's a very boring behavior. There's a run length that you move before you change direction, which is given by the velocity over the rotational diffusion coefficient. And on long time scales, it just diffuses with an effective diffusion coefficient, which is, just the velocity times the run length over 2 in 2 dimensions, and you can get the effective diffusion coefficient. Similarly, for the run and tumble particles, you just replace the rotational diffusion by the tumble rate. And then if I put an object inside the fluid, I describe it by some potential. And then the equation of motion just adds to the dynamics of the center of mass a minus mu gradient of the potential. So whenever I describe an object, I'm placing some specific potential inside the active medium. Yes?
Can you consider two-dimension just by opinions, or
Yeah, well, you could do everything in any dimensions you want. I'll comment about it, the only dimension where things change beyond the power law in a qualitative way is one dimension. But yeah, it's easy to generalize everything. And diffusion coefficients get a factor of 1 over d, right? Instead. Okay, so some things to note. First, the models are obviously out of equilibrium. This is actually important. They do not conserve momentum even in the absence of any potential. So this is now a whole class of active systems that's referred to as dry active systems. When you have conservation of momentum, it's called wet active systems. These are dry active systems. And some properties of these fluids actually rely on having no conservation of momentum. And again, this is relevant for experiments of systems moving next to a surface. That's just a name. And when you're wet, then you it's the name. I didn't coin it. Okay, it's not a very good name. Okay, it's been known for several years now that in dry active matter, if you calculate the forces exerted by a system on walls, the pressure exerted by the system on a wall, then it doesn't admit an equation of state. Meaning that if you calculate the force on walls described by different potentials, they exert a different force on these walls. And that's been verified experimentally in the lab of Olivier Duchot a couple of years ago. But nonetheless, there is a simpler class of models where you have an equation of state. Okay, these comments are more for people who've looked at these things on their own. So there are simple models where there actually is an equation of state. And if you want to understand the physics behind it, there's a paper that we wrote that was published a year ago that explains everything very cleanly. And what I want to state is that this is the class of models that I'm looking at in this talk. And actually, a lot of the very clean mathematical structure results from the fact that I'm looking at models which have an equation of state. And when that's not the case, things will be qualitatively the same, but things will not be as nice. The formalism will not be as nice. Okay, so as I promised, we'll first look at single body properties, single body inside an active medium, and then I'll put two bodies inside and extract the interactions. So this is a semicircle inside an active medium, and you know, you don't have to think a lot. These are active particles which come from here. They have an arrow, so these guys are just running into this guy, and once they're inside the semicircle, they're just pushing against the semicircle. So you expect that particles will accumulate inside the semicircle and push from the left. If a particle is coming from the right, then it has the arrow pointing in this direction, and it's going to hit the semicircle from the outside and just glide along the semicircle. Okay, so just pictorially, you can actually see that there's a force acting on this guy to the left. And there's actually a very nice experiment done more than 10 years ago where you put many of these obstacles in the middle of a chamber with bacteria, and you see that all the bacteria are actually pushed to one side of the chamber. Okay? And Jorge Kurchan, I think, has the plan of doing the experiment with fish and then getting the fish drunk so they become Brownian again, and then they can escape back to the other side. Okay. So the active fluid is exerting a force on this object inside the fluid. And the force, if you want to actually quantify it, the expression for the force is just the integral over space of the density of particles, times the force exerted by the particles on the potential. Okay, so that's a very simple expression. That's the expression if you actually want to calculate the force on the body. And what I want to stress is that in general, if you give me a model of active particles and a given potential, it's very hard to calculate the exact force that's exerted on the object. So in general, that's a very hard calculation, and I'll circumvent having to calculate it in what I present.
So you do not impose a boundary condition. You just
Yeah.
think that you have this velocity plus the force from the potential.
Exactly.
Is sufficiently smooth.
Yes. Well, I don't think it has to be. Okay, you could think about it as smooth, but okay.
If it is singular, it becomes.
I just ask the length plus length scale of this sample particle
Yeah.
and the sort of lateral dimension of the object. So these two length scales, do they have to be comparable? Because
Well, that's where you get strongest effects. Okay, so there you have to choose your object to get a large force. Okay. Okay, just as a small comment, actually, the fact that when you have a curved structure, you have a force pushing it to the right, actually implies that if you put a flexible object, a polymer, this here in the movies that I'll show you, it's a polymer with a bending and stretching rigidity, there's an instability which causes these polymers to bend. And these are polymers placed in an active medium, and it turns out that there's a critical wavelength for this instability. So if your polymer is smaller than this wavelength, it's just performing diffusion. If it's half the wavelength, you get this parachute motion, which I actually observed first numerically in the group of Ralph. If you have a longer one, then you can see that you get these S shapes where you get rotors transiently which stop. And it's much longer than it just crumples on itself. Okay, so this is just a comment, and this was actually seen in experiments in the groups of Nikta Fakhri and Jeff Gore at MIT. Okay, so back to the static object. We have an object inside the fluid, and there's a force acting on it. And by Newton's third law, if there's a force on the object is exerting a force on the particles themselves. And this force actually generates a flow. And this is a result that I won't show, but you can show that for this class of models, there's a very elegant relation between the total current flowing in the system and the force exerted on the body. So there's a tight relation. If you see a current, that you know that there is a force. And there's a very simple relation. The current and the force are obviously, from the pictures I showed you, are of opposite sign. And the proportionality constant is just the mobility. Okay, so this is something that we use in the calculations, but is not important. And what I want to again to stress that the force and current are really dependent on the shape of the potential. And that's actually hard to calculate. Now, given this, I can just think without doing a calculation. Again, we do everything in a very clean way. But if there's something that exerting a force on the particle, then if I look from far away, then the system is just diffusive with this effective diffusive coefficient. And then there's a point force acting on the medium. And actually, there's a very similar setup that was done by Tridib, Satya, and David, where they look at the SEP with a driven bond. So it's a very, very similar mathematical structure. And this equation we know how to solve. We've been to undergraduate studies in physics. And what you find out that the fluid density, which again you could think of exerting a force or a pump, is actually decays as 1 over r. 1 over r with r dot f, where f is, again, you can actually show rigorously that it's the force acting on the body, which is what you expect. And then in addition, again, this is in the far field, so it's a multiple expansion if you want. And again, the currents are diffusive. So if I want to get the current, I just differentiate this and multiply by the diffusion coefficient. And you get this simple expression with 1 over r squared. And again, this is the force acting on the body. Okay, so you measure this force, and you know the far field density and current automatically. And I want to stress that these are long range, and both the density and the current are non-local functions of the potential. This is, you see, there's a whole industry of trying to calculate steady states in these active systems, and they stop typically at the local level. But these things are generically give non-local distributions. Yes? Yeah.
Why is delta function, which is the equation, the state equation, after don't appear in the diffusive current?
What doesn't appear?
Yes.
What, sorry?
In your steady state equation, globally you have G, which is this diffusive current,
Yeah.
and you have also delta function terms.
This is just the fact that the force is exerted at a point.
So this diffusive current at the third line is except in R equals 0?
Yeah, it's in far field. Okay, it's far field expansion. Okay, in the near field, you have all the other things become messy. And of course, this description breaks down in the near field because you actually see that you have a potential, et cetera, et cetera. Okay? Okay, so this is a numerical test. These are the currents. Okay, you're looking at it. I'm lucky that it's blurred and you can't read. It's really half a decade, so you might be not impressed. But actually, we measure the force on the object, and then there's no fitting parameters. Okay, so this is a good check of things. So again, just to recap, a single body experiences a force which generates long-range density modulations and currents, and the density profile is characterized by a single measurable quantity at this order, which is the force on the object. Okay, how much time do I have? Oh. Okay. Okay, so I'm not going to show. Anyway, it's a pretty straightforward calculation. What I want to just say is, I just gave a comment that you can calculate the force on an object perturbatively in the potential. I'm actually, from now on, I'm going to use P, which is minus the force on the object, which is the force exerted on the active fluid itself. And it appears it's third order in the potential. Okay, so actually, if you're doing calculations in active matter, you start seeing interesting things. It's third order. That's my experience in all these things. And the other thing that you can notice that it's a non-local function of the potential. So it really is funny thing. Okay, so now I'm going to discuss the interactions in the time that I have left. So I'm going to take one object, which is characterized by its, so these are measured alone, the force acting on it, which is minus what I call the dipole moment of this guy. And then I'm going to put another object in the presence of this object, okay? And I'm going to put it far away in the far field away from this body. Okay, so when I do this, there are two effects. The first thing is that this body, remember, I have a density profile and a current profile. So the first thing that happens that locally here, the density near the object is changing. Okay? Now, if you remember, the expression for the force was the integral of the density times the gradient of the force. So if you change the density, you're just changing the force in the same direction. Okay, so for the non-interacting case, what you get, this is the expression for the change in density near this object, and it's enhancing or reducing the force acting on the object alone. So this is a term that's pushing you or slowing you down a bit. It's the less interesting effect, and it decays as 1 over r. You also notice that it only acts on an object which has its own dipole moment that's exerting a force on the object. So if I put a circle, there's this term is actually gone. The other term comes from the fact that this guy is now sitting inside a flow field of a current because there's a current flowing near the object. Now if I put something inside a current, there's a force that's exerted on it that is given by some, it's in the far field, so the currents are small. It's given by some response matrix, which we actually know very little about. This is very little explode, this response matrix, times the current. And this guy, remember, the current decays as 1 over r squared, so this one decays as 1 over r squared. So this guy is interesting because it can actually rotate objects. Because of this response matrix, you can actually rotate an object inside the fluid. Okay. So I'll skip this. So in summary, we have two components. We call this non-symmetric because it acts only on non-symmetric bodies, which decays as 1 over r. And then we have this symmetric guy that acts even on a circle and is related to the current and actually can rotate objects. And the important point that I want to stress is that you can express everything in terms of single body quantities. So you measure this response matrix and the dipole moment P for a given body. Two bodies, you place them in the fluid, and you know the interaction between them. Everything is expressed in terms of these quantities. And again, long range, anisotropic, and no action. And again, by controlling the shape, you can control this response function, and you can have very different behaviors. Actually, this is unpublished, but these response functions can be negative, which is a funny thing of active matter. Okay, so just to say, with pairwise interactions, the results are exactly the same. We know nothing about these response coefficients. I'll skip this. For 3 objects, you can show that in 2 dimensions and above, as long as they're in the far field, everything is additive. No problem. In 1 dimensions, things are slightly more interesting. Actually, the forces are not additive, and that's easy to understand. Okay, you can do this similar thing for torques. So if you have, for example, a semicircle that's pinned at one of its ends, then it will experience a torque that will rotate it. So it's a self-torque of this object. So you can do the same calculation for the torques, and you find out that if the object has, again, a self-torque, then it's modified by the presence of another object. And then there's another contribution from the current. And what we do is characterize it in 2 dimensions by a vector. So again, this is the object that's sitting inside a current field. And in general, there's a vector which wants to align with this current, which depends on the shape of the object. Okay, so you can characterize a response by this vector. And again, also the torques are long range, anisotropic, and there's no action-reaction. And okay, in principle, you can calculate them. Okay, so these are numerical checks. This is for a semicircle with a circle. Again, these are, it's not a lot of decades. These are numerics are Numerics are very, very painful, but there's no fitting parameters that we use here. Okay, so this is really lines through the data, and this is a check of the force, and this is a check of the torques, and this is again for two objects where each of them has a dipole moment, and everything works very cleanly. So a few comments before I go on. It's easy to extend this to higher dimensions. You just change, you just add. You add for 3 dimensions, you add 1 wherever you see power law and factors of pi. Another interesting thing is that even if you place 2 rods inside an active medium, and that's a problem that's been studied before us numerically, but people only focused on the near field where sort of the active particles don't have time to diffuse, so they hit one wall, come back, and that creates a short range effect. But actually, if you think carefully, if you have a flat object inside an active fluid, it generates a quadrupole moment. Okay, and that quadrupole moment also generates long-range interactions between objects in an active fluid. And you can argue, we can't calculate and write down expressions for this at the moment, but you can argue that it decays as 1 over r cubed, and these are numerics which are at least consistent with this result. So except for infinite flat walls or circles, everything interacts through long-range interactions in these things. And again, all the calculations are done in this adiabatic limit, so when they're not moving the objects. Okay, so how much time, David? 4 plus 5. Okay, let me try and explain at least one of the movies that I showed you. Okay, so what I'm going to do is, you remember I showed you at the beginning of the talk that if I take 2 semicircles and I pin them and I tune things correctly, they start rotating in the same direction. So what I want to do is argue why that happens. Okay, so let's take 2 types of semicircles. This one is pinned and rotating about the center. This one is pinned and rotating about the apex. So I'm going to call them C for center and A for apex. Now, I induce an outside current on this system, and you can, without doing any calculation, you can convince yourself that if the current is flowing this way, if you're rotating around the apex, then this object would like to align in this direction because the current is sort of pushing these guys. It's sort of gliding and pushing these guys in this direction. And if you're rotating about the center, then you want to align in this orientation with the current. Okay, so again, this is gamma for this. So if you want, gamma here is pointing to the left, and here it's also pointing to the left. Okay, understand. Okay. So type C and type A align differently with the current. And now what I want to do is start looking at different cases. So let's start with 2 center pinned semicircles. So what I've denoted here is, in this purple, is the current generated by the other object. So if I have this object, it's generating a current that's flowing like this. So this guy is feeling a current in this direction. Okay? And this is gamma, the vector that's telling me in which direction I want to align with the current. And you can see that in this configuration they're happy, and in this configuration they're happy. Both of them are generating currents where the other guy is happy with it. So this is a movie. Again, I'm not showing you the active particles. And you can see that, in fact, they're quite happy. Of course, there are fluctuations. They're quite happy in this configuration. And this movie, I want to stress, has higher multiple effects, but the leading order behavior is captured by I show you. And if we wait long enough, which given the time that I have, I'm not sure we can. Okay, but eventually they flip and they find also this configuration. Okay, so these are 2 stable configuration for 2 center pinned objects. If we have 2 apex guys, that you can easily convince yourself that they're happy when they're pointing this way, because this guy is generating a current that flows like this. This guy is generating a current that flows like this. So the stable configuration in this one and the reversed one. Okay, so if you throw these 2 guys, they align different than the other guys. Okay, now if I take and if I mix them, then you can see that if I have this configuration, then nobody's happy. Okay, and I have this configuration, nobody's happy. Okay, so they're never quite happy with each other when I mix a center and an apex guy. So what happens is that if one is much less mobile than the other, then the fastly rotating guy is just, its motion is dictated by the slowly moving guy. So you have phase locking. So this is a case where the A has a slower rotational diffusion, and that's actually so A is green. So you can see that this guy is actually dictating the motion, and this is just the opposite picture. Okay, I'll show you it because I don't have enough time. These are actually movies, and you can see that in general, you have this phase locking where the slower rotating guy is dominating the motion of the fast rotating guy. But when their rotational mobilities are comparable, then they're sort of in this, nobody's winning, and that actually causes this co-rotation. And you can actually write down, using the equations for the torques that I wrote before, you can write down simple equations of motion for these two coupled rotors and predict that you have this moving thing. Actually, just to sort of sell off, actually, we wrote down the equations, predicted this, and then saw it in numerics. Okay, and then I think I'll skip this guy. Too much detail. So just to summarize, so what I've done is I've first looked at a single asymmetric object in an active bath. And I think it's important that if you put something asymmetric in an active bath inside a cell, then it doesn't generate a local effect. It generates a really long range effect, which is something that's often completely ignored in the modeling of these things. Motion inside cells and things like that. This generates long-range modulations and long-range interactions between objects inside this fluid. For this simple models, we could express this in the far field in terms of single body properties. And you can show that these results hold without interactions or with pairwise interactions. We're now trying to extend it to more complicated interactions. There's tons of handles that haven't been explored here. First, torques on active particles, non-pairwise interactions. We know nothing about the response functions, and they have really funny behavior. Nobody's looked at them numerically or analytically. We've done it in 1D. We haven't published that. What about near field? There must be some interesting near field interactions which would generate interesting things. And again, you can control interactions by the shape. So a natural question is, can we throw a bunch of these guys into a fluid and make them self-assemble into something interesting? So build a house or something. Okay, probably too ambitious, but do something interesting. And of course, resetting. Okay, this joke didn't fly. Okay, so this is, I'll just close. This is a bunch of these C-typed semicircles thrown together inside an active fluid. And you can try and guess what will happen. And while I finish, I'll let it run and you'll see what happens. So thank you very much. Yeah.
This seems rather specific.
No, okay.
Can you have some sort of symmetry parameter to characterize any object?
Yeah, so everything's expressed in terms of this dipole moment. And what we found out numerically is that semicircles give the very large dipole moment because of their shape. Yeah, but it also, you could put any other shape that, okay, there's two reasons for doing the semicircle. One, we wanted to avoid things with self-torque that would start rotating on their own. But even if you obey these symmetries, we wanted for the numerics something that generates a strong dipole moment. And we just found out by experiments that a semicircle generates a very strong dipole moment. But the results hold for any shape Okay, as long as you don't have a symmetry, that's it.
Yeah. So just wanted to clarify that. So this information about the active medium, that will give the amplitude of 1 over r square, is that right?
Yes, yes,
So,
yes.
and then it's totally universal in the sense, no matter whether it's active Brownian or non-Dumble, anything.
For what we've done, it's exactly the same thing. Everything's encoded in this dipole moment, and this dipole moment depends on, its magnitude. Run and tumble or active Brownian particles will be different. The shape of the potential will affect it. So it really depends on the details of the modeling, and the trick is to avoid it because calculating density distributions for an arbitrary potential is really hard in these things, as you know.
They reached
Yeah.
stable state. Is it guaranteed, or could they just go on forever in some cases?
Oh, okay. So I showed you the rotating guys. Okay. So that it could be a non-steady state. Yes. So we can do all the calculations without interactions and with pairwise interactions. Yeah, so that's what I want to stress, that typically you're slightly ashamed of doing calculations in the non-interacting limit. Okay, I'm exaggerating. You're not, okay, but you sort of feel manly when you do interactions, right? But, okay, that's not politically correct these days. Okay. Okay, yes. But that's what I want to stress here, that these interactions, they're not like Casimir effects, where you have to fine-tune things and you build on interactions. These occur even when you have a non-interacting fluid because they're generated from these currents, which are generated even if the active medium is non-interacting. So it's a very robust effect. You see, it's very hard, whatever you do, if you're pushing locally on the particle in a far field, it will look like this. It's very hard to avoid that, at least when you're in a disordered phase.
Okay, last question, Eli.
This question, I think in the cell, an interesting question would be when you pull these active networks, so you have a long kind of spaghetti moving close to the particle. That would, I think, maybe will lead to other forces than what we talked about.
So
Geometry, because you have these pulling events, that's
So pooling will definitely change things. Gleb has done it. Where's Gleb? Anyway, he's done it for. There's interesting effects even when you're pulling passive particles. Okay, but you're right that there's interesting things too.
not only the pulling, it's the fact of the geometry of the.
Yeah. No, I agree. Okay.
Okay, so I'll start by thanking the organizers for inviting me to speak here. And I'll talk about active Brownian motion in 2D. And this work was done in collaboration with Satya, Alberto, and Gregory, all of whom are here. And this was done when I was a postdoc in LPTMS last year. So this is the outline of this talk. I'll briefly introduce active particles and active matter, which was mostly already done in Yariv's talk, so I'll just go very quickly through it. And then I'll introduce this active Brownian particle, the particular model that we are going to talk about. Again, Yariv already introduced it, so it will be easy for me. Then I'll talk about the behavior of a single active Brownian particle in free space, particularly focusing on the short time regime. And we will see that the signatures of activity are particularly present as in the form of anisotropy and anomalous persistence properties. And then I'll go on to a single active Brownian particle in presence of an external potential and see how the dynamical evolution and the stationary state shows the signatures of activity. So active matter, as Yariv already said, it's a collection of self-propelled active agents, each of which can generate directed motion, consuming energy from the environment. So basically, they're intrinsically driven out of equilibrium. And this study of active matter is relevant in a wide range of disciplines, starting from biological systems, soft matter, and even social transport. So there are examples of active matter both in nature and also there are artificial examples. So for in nature, There are these so fish schools or bacteria or this flock of birds. They are all examples of natural active agents. So in this case, a single fish is an active agent, and this formation of fish school is a collective behavior of these active agents. And also there are artificial or man-made micro or nano swimmers, these genus particles or genus rods, all of which are examples of active particles. So this active matter shows a lot of novel collective behavior, like swarming or flocking, as we saw here. So this is an example of flocking. Also motility-induced phase separation, and even absence of well-defined pressure or absence of equation of state, as Yarif already mentioned. But the surprising thing is that even at the single particle level, these active Brownian particles show rich behavior, like non-Boltzmann stationary state and anomalous dynamics. So this is what I am going to focus on in this talk. So there are dozens of different models of active particles, like Yarif already mentioned, active Brownian particle, RTP or random-tumble particles, and there are several other models. So in this talk, I'll just focus on the very simplest one, the active Brownian particle. And here the activity comes through the coupling of the spatial motion with an orientational degree, which undergoes a rotational diffusion. So I'll just define the model a bit more clearly. So active Brownian particle describes overdamped motion of a single particle which moves with a constant speed v0, and it has an orientation of its own. So it moves along some particular orientation phi, and the orientation itself can change. So in 2D, the configuration of the whole system is given by its position xy and the orientation phi, which itself can change, and in this case of ABP, it changes through a rotational diffusion. So the Langevin equations describing the motion of this particle is this set of equations. So what it's basically what Yarif wrote in the vector notation. So here I write it in components explicitly. So x dot is v0 cos phi t, v0 is the constant speed, y dot is v0 sin phi t, and phi dot undergoes a ordinary Brownian motion with some rotational diffusion constant dr, and eta phi is a white noise delta correlated. So throughout this talk, I am going to consider the initial condition that the particle starts at the origin, oriented along the x direction. So x and y both are equal to 0, and phi is also 0 at time t equal to 0. And so it has, I mean, this model has been studied in a whole lot of works in various contexts, and I just listed a few here. So there is a very nice interpretation of this motion, a nice geometric interpretation, which is due to David Mumford. So let us consider a curve where the curve length is given by t, and let us think that so this tangent vector t makes an angle phi with the horizontal axis x, and let us consider that the local curvature is given by some random number eta, which is again white noise. So we see that the infinitesimal increment which generates this curve is of this form: delta x is cos phi delta t, and delta y is sin phi delta t. So this is nothing but the dynamics of this active Brownian particle that we saw here. So if we just integrate with this small time delta t, we get this equation. So this the trajectories of a single ABP is nothing but a curve generated with random local curvature, and one can write a Fokker-Planck equation for this process. However, there is no exact solution known till date. So before before I start discussing ABP, it's good to have a quick reminder of the passive Brownian particle, which is nothing but ordinary Brownian motion. So in this case, in 2D, both x and y component evolve with some independent white noise eta x and eta y. D is some diffusion constant, the translational diffusion constant. Eta x and eta y, as I said, are white noise delta correlated. So here the important thing is that eta x and eta y are uncorrelated. So x and y coordinates completely decouple, and starting at the origin, the average position remains at the origin at all times. However, the mean square displacement grows linearly in time for both x and y components, and the distribution is Gaussian at all times. So we will keep on comparing this ABP with the ordinary Brownian motion. So one can recast this ABP dynamics in a similar form like the ordinary Brownian motion. So here this xi x and xi y are the effective noises, which is nothing but this v0 cos phi and v0 sin phi, with phi performing this ordinary Brownian motion. So this effective noise is very different from the white noise on two important counts. So first thing is that it's bounded at all times by this speed v0. And secondly, we see that this xi x autocorrelation of this noise is of an exponential form. So it's not a delta correlated noise anymore. It has an exponential decay with this rotational diffusion constant dr, and xi x, xi y and yy also have similar form. So what we see here is that due to this form of this correlation, there is a time scale dr inverse which is introduced in the system, and that gives rise to two distinct time regimes, short time and long time regimes. So let's look at the trajectories in these two time regimes. So for long time, we see that this correlation actually decays very fast. So one can expect that this xi x and xi y are like white noises. So some sort of diffusive behavior is expected. This is also what Yarif showed in the movie. So at long time, if we compare trajectories of ABP, so this is ABP and this is ordinary passive Brownian motion, they look very similar. Both of them are diffusive. The ABP actually one can show mathematically that this performs ordinary diffusion with an effective diffusion constant, which depends on V0 and dr. However, things become very different when one looks at the short time regime. So when t is much smaller than dr inverse. In that case, so this is the trajectory, one example of a trajectory piece of ABP in the short time regime. And while PBP still remains same, it's still diffusive, ABP shows a very different behavior. So this is the effect, this is the signature of the activity, which comes because of this presence of time scale and the coupling of the orientation with the positional degree. So this is, as I said, this is an important signature of the activity, and what I'm going to do in this talk is to look at how this changes the position distribution and persistent properties compared to the ordinary Brownian motion. So this work is reported in this paper, which is on arXiv. Okay, so to do that, let us first look at the very simplest things. Let us look at the first two moments. So what we see is that contrary to ordinary Brownian motion, where both x and y average were 0 at all times, here x average saturates to a different non-zero value, while y average stays 0. So this first indicates the presence of an anisotropy. So x and y components, even though they have this cos and sine, which look very similar, but they have this different behavior as time goes on. And this is again reflected in the mean square displacement. They also have different expressions for x and y components. And this is most prominent at the short time regime. So this is a plot of sigma x square and sigma y square separately, and we see that at short time they behave very differently. So sigma x square goes as t to the power 4th, while as sigma y square is t cube. On the other hand, in the long time regime, both of them go to the linear diffusive behavior with some diffusion constant. So the next natural question is to ask what happens to the distribution, the position distribution of this particle, and there is no exact result known so far. So this is what we are going to do. We are going to look at the short time regime, that is the time much less than dr inverse, this intrinsic time scale, and we will try to see what is the position distribution of this particle. So in this short time regime, one can actually write a set of effective equation of motion. So remembering that for short time, this phi is also very small. So one can expand this cosine and sine in terms of phi for small phi, and that gives this effective equation of motion. And indeed, these equations are also very anisotropic, and this is reflected in the distribution. So this is pxy at some time t, which is much smaller than this time scale dr inverse 10 here, t equal to 1. And what we are going to do is that we are going to analyze this marginal distributions pxt and pyt in this short time regime separately. So let's first look at pxt. So this is the effective equation, which is quadratic in phi square. Phi again is the ordinary Brownian motion, the rotational diffusion. And we see that this xt can be expressed as a Brownian functional, and one can use path integral techniques to find pxt. By calculating the Laplace transform of this Brownian functional, and it turns out that it can be calculated exactly. It has this form, and more surprisingly, it can even be inverted exactly to give this scaling form for pxt with this scaling function, which is given by this complicated sum. The exact form of the sum is not important, but what is important is that one can extract the asymptotic behavior of the scaling function at both the regimes. So this is a plot. So the solid line basically shows the function given here, and we have collapsed the data for different value of t all in the short time regime according to this scaling form, and it gives a perfect data collapse. So we have this exact expression. And one can now go to the short time behavior for pyt. In this case, the effective equation is linear in phi, with phi dot given by eta phi. And one can see that if we take one more time derivative, it can be recast as a random acceleration process, where y double dot is proportional to white noise. And random acceleration process, so I'll just make a quick detour to random acceleration process. It's one of the simplest non-Markovian processes. Non-Markovian because the acceleration depends on the white noise instead of the velocity. And it shows very different behavior than ordinary Brownian motion. It has a Gaussian distribution, but the variance is not t, but t cube. And it also has non-trivial persistence behavior. So random acceleration process has been studied for over 60 years. And so there's a nice review by Satya, Bray, and Gregory in 2013. So what we can do is that we saw that our active Brownian particle, the y component of it, can be mapped to this random acceleration process. So we can predict the short time properties of the y component using the known properties of this RAP. So this is what it turns out to be. So pyt in this case is very symmetric around the origin, contrary to the x component, and it actually has a Gaussian distribution of this form. So with the sigma y square, which is t cube, as we also saw previously. And here the solid line is just a standard Gaussian distribution with the sigma y of this form, and the points are different values of t, all in the short time regime again for some values of dr, and we again see that this is a perfect data collapse. So this gives the expression for y marginal of the active Brownian particle. So I'll just do a quick recap. What we saw so far is that we can calculate exact marginal distributions pxt and pyt in the short time regime for an ABP. And the next natural question is to ask whether one can also calculate the radial distribution. And the answer turns out to be yes. So we calculate the radial distance r squared. And this again can be expressed as a Brownian functional, and one can use the same similar path integral technique to calculate the Laplace transform of this quantity, this z. And again, it can be inverted. The expression is much more messier this time. It's this series sum, but important thing is that it has this scaling form, and one can again extract the asymptotic behavior of this scaling function. So this plot shows p of r squared t scaled according to this form, and the solid line is the exact calculation, and once again we see that it's exact, it's matching perfectly. So the next question we are going to ask is the persistent or first passage properties of this active Brownian particle. Persistence properties play an important role in characterizing stochastic processes. So here what we will do is that we investigate survival in presence of absorbing walls either at x equal to 0 or y equal to 0, and we will look at the survival probability, which is the probability that the particle or ABP is not absorbed in these absorbing walls up to some time t. And we will compare it to the ordinary Brownian motion, where the survival probability always goes as 1 by square root of t. So let's first look at the case where there is an absorbing wall at y equal to 0. So this is our particle. It always starts aligned parallel to the x-axis, and we have this wall at y equal to 0. And we start from some initial position y naught. The initial position along x doesn't matter. And we look at this survival probability sy, ty0 I call. And in the short time regime, one can predict the behavior of syt using the results of the exact results of random acceleration process, which is already known. And so this is the exact result, and it decays as t to the power minus 1 by 4. So this was calculated as in these works previously, and changing it to our units and our system, this is what we get. This is the exact survival probability of the y component. On the other hand, so this is valid for short time regime only, because the mapping of ABP is to RAP is valid for short time only. Yes.
When t goes to 0, this quantity diverges.
Yes, this is valid. Yeah, so this expression is valid for t much greater than 1, but t much less than dr inverse. So for RAP, it's valid for long time regime. So in our case, the mapping to RAP is valid for short time regime. So this result actually is valid in our case for t much larger than 1, but still t much less than dr inverse. So in this interval,
Which means that dr must be
very small.
much smaller than 1.
Yeah. Dr must be very much smaller than 1 for us to see this this regime really. On the other hand, when t is much larger than dr inverse, we expect an effective Brownian behavior, because the noise correlation decays, and we have seen that in this case the particle behaves diffusively. So this is what we see here. So yeah, here in this very small time regime, so what you were asking, there is a little mismatch. On the other hand, so dr is really very small here. So we plot the survival probability as a function of t for different values of dr, all very small. And we see that in this intermediate regime, much larger than 1, but still much less than dr inverse, we have this t to the power minus 1/4 decay, and which crosses over to this t to the power minus 1/2, the diffusive behavior. And so looking at this behavior, so this crossover is expected at some time t equal to dr inverse. And looking at this behavior, one can propose a scaling form, which is of this form. So we have this 1/6 power of y0 dr over v0, and then function of t dr. So this is our dimensionless quantity. And we see that all these curves that we saw here, these curves for different values of dr can be collapsed perfectly with this scaling form. And this scaling function has this behavior that for very small argument, it's u to the power minus 1/4, and for large arguments, it's u to the power minus 1/2. So random acceleration process to Brownian behavior. We can now look at the survival probability of the x component. So again, we start with an orientation parallel to the x direction, and now there is an absorbing wall at x equal to 0, and we look at the probability that the particle is not absorbed by this wall up to time t. And we remember that the effective equation for short time was this. So for very short time, the velocity is almost constant, so it's like a ballistic behavior. So one can expect that the survival probability doesn't change much, it stays constant. Whereas at long time, this equation is not valid anymore, and we can again expect a crossover to a Brownian-like behavior. And this is what we see for different values of dr, again much smaller than 1. And one can also propose a scaling form, which is much simpler now. So it's just a function of t dr, and this is what we see. So our scaling function is just constant for short values of the argument, for small values of the argument, and it goes to a Brownian behavior for longer time. So how much time do I have, David? Okay, so let's go.
In the both cases, you have some constraint on x naught in this case and on y naught in the previous case, right?
Yeah, so this result is valid for y naught very small, but the scaling collapse and these things will not be dependent on the x naught and y naught.
No,
So
but
yeah.
t and y naught are somehow related.
Yeah, okay, yes, in that sense, yes. To see it, we need to have to be within the regime, yes. Okay, so what we saw so far is that we studied the active Brownian particle, its motion in free space, and we saw that there are strong signatures of activity at short times, which manifest as anisotropy in the motion and non-trivial position distributions, and also anomalous persistence. And we saw that in all these cases, the behavior crosses over to a passive Brownian one at times much larger than dr inverse. So one can ask the question that is it possible to see these signatures of activity at long time? And the answer is yes, but then one has to put the particle in an external potential. And this is what we are going to do in the remaining time. So we study the dynamics of an active Brownian particle in a harmonic potential. So there have been many studies, numerical studies and also experiments for this kind of system, and it's known that there are strong signatures of activity at long times which manifest as non-Boltzmann stationary state and which crosses over to Boltzmann-like state. So this has been studied in these works before, but so far there are only qualitative understanding and there was no exact result for this transition or crossover. So before going into the mathematical analysis, let me just briefly describe an experiment that was done recently by Takatori and group in 2015. So they studied confinement of self-propelled Janus swimmers, which are active Brownian particles, in a harmonic-like acoustic trap. So in the dilute limit, their system is equivalent to a collection of non-interacting active Brownian particles. And what they saw is that the stationary profile of this collection of particles shows a transition from Gaussian-like or Boltzmann kind of behavior to a very non-Boltzmann behavior when one varies the trap strength. So for weak confinement or weak trap strength, so which corresponds to the passive limit, in this case the stationary profile is very much Gaussian-like or really the Boltzmann one. On the other hand, when the confinement is much stronger, so this is our strongly active limit, in this case what they saw is that the particles cluster at a distance away from the origin, away from the center of the trap. And this is a signature of activity. This is definitely non-Boltzmann. This is what we will try to understand in the rest. So in our case, we study active Brownian particle in a harmonic trap of strength mu. So this is our potential, and one can write again a set of Langevin equation for this ABP in this potential. And now we see that there are two competing timescales. There was this internal timescale dr inverse already present in ABP. Now, because of the presence of this trap, there is an additional timescale which is mu inverse, which controls the relaxation within the trap. And we can expect some anomalous behavior because of the competition between these two timescales. So just a quick reminder that for a passive Brownian particle in a harmonic potential, there is only one timescale, this mu inverse, and in this case it's just an Ornstein-Uhlenbeck process which gives rise to a Gaussian stationary distribution. So in this case, depending on which timescale is larger, we get two very different time evolution. So for very short time, one can actually ignore the effect of the trap. The particle has not seen the trap yet, and it is described by the short time behavior that we already saw. It has this sickle-like position distribution concentrated at some angular region. However, as time proceeds, depending on whether mu inverse is larger than dr inverse or not, we get to very different kind of evolution. So if mu inverse is larger than dr inverse, it means that the rotational degree, the orientation relaxes quite fast. It doesn't retain the memory of the initial orientation, and the particle behaves more or less like an ordinary Brownian particle. So it diffuses quickly, it becomes isotropic, it loses the anisotropy that was in the initial condition, and in the stationary state we get a Gaussian-like behavior centered at the origin of the trap. On the other hand, if dr inverse is much larger, which means that the particle retains its memory for much longer time, in this case the anisotropy continues and the particle tries to go away from the center of the trap, and only when it reaches the boundary then it slowly diffuses and becomes isotropic, but it still is very different from the Gaussian behavior. It is centered away from the origin. The particle almost never reaches the center of the trap. So this is our strongly active regime, and this is the strongly passive regime. And if we look at only the stationary state by varying this dr, our time scale, we see a crossover between this Gaussian behavior, which is for very large dr, to this clustering at the origin through some intermediate state. So what we will do here is so there is this stationary crossover. And one can of course write a Fokker-Planck equation in the presence of a harmonic trap to describe this full probability density, which is a function of p, x, y and phi. However, it's not easy to solve. In general, it's not solvable in fact, and we will follow an approach which was introduced by Grether, Dornick and Luke in 2011 in context of complex Brownian functionals. So we will not look at the solution of the Fokker-Planck equation, rather we will look at the moments, and so for that we introduce complex notation. So z and z bar, x plus iy and x minus iy, x and y are our position components. And one can recast the Langevin equation in terms of z, this complex coordinate. And yeah, so I'll just mention that even though so the process that they looked at in their paper, that's very different than our active Brownian particle. However, the radial moments are same, but I mean it's not very important at this context. So the point is that we look at these moments mkl, which is z to the power k and z bar to the power l as a function of time t, and it turns out that one can write an exact time evolution equation for this mkl, which is time dependent. I mean the right hand side is explicitly time dependent. So it's not even possible to solve this equation for the stationary state directly. But what one can do is that one can calculate any moment recursively using the initial conditions. So for any kl greater than 0 at time t equal to 0, mkl has to be 0 because we start from the origin. On the other hand, m00 is 1 at all time t. So using these initial conditions and using this equation, we can calculate any moments recursively. So mkl depends on k minus 1l and kl minus 1, these two quantities. But the question that we are interested in is the probability distribution. And again, as I said, I mean this equation is very difficult to solve in general. So what we will do is that we will look at two limiting cases. The strongly passive case where dr goes to infinity, so the particle relaxes almost immediately, I mean the orientation relaxes almost immediately, and the strongly active case, dr going to 0. In this case, the particle remembers its initial orientation for a very long time, and one can expect a non-Boltzmann behavior. So the signatures of activity would be most prominent in this regime. So let us first look at this passive limit, dr going to infinity. In this case, dr is large, so as we saw that the evolution becomes quickly isotropic, and we can expect an effective Gaussian behavior. And it turns out that in that here this mklt can be solved exactly for all time for any values of k and l, and it has this form. So from here one can calculate the radial moments, which is just putting k equal to n, so it's a function of z bar r square. So this is the form of radial moments at all time t, and one can show very easily that this is consistent with the Gaussian radial distribution at all times. So this is the form of the Gaussian distribution. So in this passive limit, when dr is very large, the radial distribution of this active Brownian particle in a harmonic trap remains Gaussian at all times, and of course the stationary state, which is given by the large t limit, it remains a Gaussian, which is of this form. So you can see that this is like the stationary state of an Ornstein-Uhlenbeck process, but with an effective diffusion constant, which is this dr by v naught square by 2 dr, what we had before, also in the free particle case. So this is a plot of pxy in the stationary state in this regime. And on the other limit for this dr going to 0 case, so as I said, I mean the persistence time is very long, and the particle remembers its initial orientation, so it just goes along this orientation and hits the boundary of the trap, and then only it starts slowly diffusing. So in this case also moment equation can be solved exactly at all times, and we calculate the radial moments, which are of this form, and the distribution at any time is given by a delta function. So this delta function, which is moving for short time, one can see here that the delta function moves at in a ballistic manner, so there is a constant velocity v naught, and the stationary distribution is when the particle reaches the boundary, and it's just all the particles are clustered. I mean our single particle is most likely to be at the boundary of this trap, and this is the form of the stationary distribution. Okay, so the next question is intermediate dr. So in this case we don't have an exact solution, but one can do a perturbation around the passive limit. The strongly active limit is actually non-perturbative, and one can do a perturbation around this passive limit, and what happens is that physically, so there is this strong peak, the delta peak around the boundary, and as dr is increased, the peak starts to widen and it also starts to move closer to the origin, and this is what we get. This is numerics, this is what we get as the stationary distribution. So I'll just conclude quickly. So what we have seen is that we have studied the active Brownian motion in 2D, and we have seen that it shows a diffusive behavior at long times in free space. However, at short time there are strong signatures of activity, which is manifest in anisotropic behavior and also anomalous persistence behaviors. And we could calculate the exact distribution at short times. And we have also studied ABP in presence of a trap, where we saw that the signatures of activity can be made to stay up to a long time limit in the stationary state, and we have found the exact results in 2 limiting cases. So there are still some open questions. So first thing is that if it's possible to see analytically this crossover from short time to long time regime, this we have not been able to do yet. And also it would be very nice if we can see experimental verification of our short time predictions. These are very non-Brownian things, and it would be, it might be possible to see really in experiments. And of course the next question is to put interaction, if one can solve analytically interacting ABPs and see what their behavior would be. So thank you very much for your attention.
Something about oh, there was a question there?
Yeah, what is known on the velocity distribution of these systems?
Velocity distribution in what sense? So this is always moving with a constant speed. And the direction of velocity is just the phi, so it's Gaussian. So these are overdamped particles, so there is no velocity as such. In the experiments, they also consider the overdamped limit. So, but there are models of underdamped active particles, and in this case, the velocity also shows in some models, the velocity also shows a distribution like this. In some of the there is these depot models, and where they basically have a velocity dependent how do you call it? What do you call this gamma? Friction, yeah. So velocity dependent friction, and in that case they have studied the velocity distribution, and in some cases this shows this 2-peak structure or this kind of behavior. So in underdamped models it has been studied numerically.
So just a remark, we should discuss it since we worked on very similar problems.
Okay, yeah, okay.
We managed to solve the Fokker-Planck equation that you mentioned at the beginning.
So the Fokker-Planck equation of free
ABP. The price
Okay.
is that you have to expand it in special eigenfunctions, which are Mathieu functions.
So the Fokker-Planck equation in full x, y, phi. Okay.
In Fourier space, so you do a Fourier transform with respect to the position, and then it reduces to something that's reminiscent of the quantum pendulum.
Okay, and do you use some approximations like first Fourier, the full thing? Okay. Oh, that's great.
Just a small question. When you solved for the short time behavior, you used the small angle approximation.
Yeah.
So I would expect it will only give you typical fluctuations, but you compared also the tails.
No, why do you say that? I mean, we are just doing an expansion, so phi itself goes as square root of t, and then we are writing an effective equation of motion with this expansion, and that should give the full distribution in for short time. Why are you saying that only typical?
Well, because you have also probability for large fluctuations, even at short times of phi.
Yeah, but that's contained in this effective equation, right? Why are they not
Okay, so
contained?
maybe I didn't understand.
But the problem is very nice because all distributions in reality are bounded. So what you get is
Yes.
the background. It grows with the time.
Yes. Yeah, and that's that's the collapse. I mean, with this t square and t cube sort of.
More questions or comments?
Passive. Yeah. So this is, this is not, there is no perturbation here. It's just a plot from numerics. But the perturbation one can do only from the passive limit. I just described physically what happens is that when one increases dr, so this peak starts to widen and then starts to move closer to the origin. But you can also say that, okay, when you go from the passive limit, peak starts to, a deep starts to at the origin, and then it moves away from the origin. Yeah, the active limit is very non-perturbative.
I have forgotten under what conditions, but there is an intermediate situation where you have a
A ring and the peak in the middle. No, we haven't seen something like this. Either we have a peak in.
Not into, I see,
In this case, no.
because I badly remember.
For active particles. For active particles, you mean? I mean other models. Okay, okay.
More questions? Okay, so let's thank Ola again. We'll convene at.
So first of all, I want to thank the organizer for the invitation. It's been very interesting. I didn't know how this conference will go. I just knew that there are very good people and it should be interesting. And it turned out that it is actually very interesting. So thank you. I will be talking about vibrational systems, and of course it is a special privilege to talk about vibrational systems in PISA, because probably this is the most important vibrational systems that in the history of science. This pendulum in the Duomo, which was used by Galileo to observe that vibration period is independent of the amplitude. Now, the truth is that this chandelier has been replaced. I was looking at it for some time and it didn't vibrate. And then my Italian friends told me that actually the original chandelier was much lighter, and therefore apparently the wind in the Duomo was making it vibrate, and this is what enabled the observation, which led to invention of clocks, which led to cosmology, to our GPS system, to everything, navigation, everything is based on and came out of this observation. So I will be talking about vibrational systems, and today, the emphasis has moved from this huge chandelier to very small systems, which I call mesoscopic oscillators. And I give a few examples of these systems. So their major feature is that they are sufficiently large so that you can observe them individually. And at the same time, they're sufficiently small so that fluctuations and nonlinearity come into play, because vibration amplitude becomes kind of comparable with the size already for small amplitude, and this means strong nonlinearity. So here are some examples. One is a carbon nanotube. Carbon nanotube is essentially a sheet, a monolayer of carbon wrapped into a tube, and the diameter of this tube is a couple hundred angstroms, and the length can be half a micron, and then this is think of a string in a violin, and it vibrates, except that you can't hear it because it vibrates at a few hundred megahertz. Another example is an electron in a cavity, and this electron, it's a centimeter-sized cavity. This cavity is used for fundamental measurements. The G factor has been measured using this cavity to the current precision, I think 12 digits or something like that. And another example, so this is a mechanical system. Yet another example is an electromagnetic mode in a cavity. And the mode is also an oscillator. And this is a big issue now in quantum computing. These are where these modes are used today, microwave modes. Yet another example are called atoms in traps. And these systems allow you to study classical and quantum many-body physics far from thermal equilibrium in the situation where the systems are well characterized, so you can really know what the system is. This nanotube is you can see it. This is a real picture. So these systems, in the context of my talk, are probably the first, definitely the first, and I want to hear from you if you know of better systems or alternative systems where rare events could be quantitatively characterized far from thermal equilibrium, where there is no detailed balance and you can measure a rare event in the system and calculate the probability, calculate things. So far, I know only of this system that can be used, and I will talk about it in a second. But before I start talking about it, I want to talk about the term that I learned just actually 2 weeks ago, which is called the Schrödinger bridge. And today is very important to put a tag on what you are talking about. So this tag was invented to describe this question that Schrödinger posed in 1931, that if you have particles Brownian particles at time 0 in one state, and then in time 1 in a different state, what was the trajectory? How did particles evolve from one state to another? Now, blessed be ignorance, we didn't know about this Schrödinger question. We asked this question for rare events some 60 years after Schrödinger. And let me show you the observation which has been done with these vibrational systems, and I will talk more about it. So imagine that you have a system that has 2 stable states. So this is not really a potential, but for the time being, let's think that this is a potential. And you can have a particle in this minimum and can make a transition as a result of a fluctuation from this minimum to another minimum. So you have a noise-driven particle, and the equation Q are just dynamical variables of these particles. K is the force on this particle, and F is noise. So you ask yourself, what happens if this noise causes the particle to make a transition from one state to another? If there were no noise, the particle would be sitting at this minimum or at this minimum. Now, the noise causes transitions. If the noise intensity is small, these transitions are rare. And you want to calculate the probability of this transition. Essentially, what you know is the probability density functional of the trajectories of this noise. So noise is something that is the source of fluctuations, and you know the probability density of realizations of different noise trajectories. So suppose if Gaussian noise, then pi is just a quadratic functional of f of t. Now you want to find the realization of the noise that drives your system from one stable state to another. So what you have to do is to find what is the most probable realization, because if the noise intensity is weak, most likely this noise will not cause a transition from one minimum to another. Most likely it will make the particle fluctuate about the stable state. Now, if it nevertheless does move the particle, it's a rare event, and you want to find the most probable realization of this event. So essentially you have to minimize this functional with the constraint that the system moves from one state to another. So essentially you come to just a simple problem of finding the extremum of this functional, of which pi, plus you add the Lagrange multiplier, and this is probably one of the most, to me, it's the most convenient formulation, because it allows you to study switching, to study just large deviations from a stable state to another, to any point in phase space of the system. So you find this extremum, and if this extremum exists, it means the following, that when the system makes a transition from one state to another, it most likely moves along a certain well-defined path. And what you do is the following in the experiment, and this is the experiment done with the vibrational system, I will talk more about it, is you say, okay, well, I observe my system in this state, and then I just take a record of the trajectories. Now I found that my system has made a transition from this state to the vicinity of another state. Okay, I keep this trajectory in my memory, do the reset. I put my system again here, and again I wait, ultimately make a transition. I record the trajectory and do it over and over and over again. And I have a record of these trajectories. Now I just superimpose these trajectories on top of each other. And this is the distribution of the trajectory that are followed by the system. Now I don't know if you can see it. At the bottom, this red line shows the theoretical trajectory which corresponds to the extremum of this functional in phase space. So these are two dynamical variables of the system. And these experimental points of the maximum of this distribution lie just on top of this theoretical line, which is kind of not surprising. Now, what is the object that you are calculating if you want to calculate it? The object is essentially a conditional probability that the system was initially at time ti in the vicinity of this state, some point qi, and the results hopefully will be independent of qi. Then at time tf, it was somewhere in the vicinity of this stable state. And you look at the probability density for the particle to go through point q at some intermediate time t. And if you choose times wisely and integrate over the vicinity of this state, you will see that this probability density corresponds essentially to the probability flux. And this flux has the form of a Gaussian tube. Psi perp is the direction transverse to this tube of trajectories. And the trajectories move with certain particles move with a certain velocity along this optimal trajectory, which you can also calculate. So this is, and W is just the rate of switching, which you use to normalize the probability flux. So this is the object that you calculate, and you can calculate it here, and you calculate it there, away from the saddle point. And if somebody knows how to calculate it in the vicinity of the saddle point, I would be very grateful and excited to see how to do it. I don't know how to do it. Anyway, this is the observation, the experimental observation of the optimal path, which is essentially the experimental confirmation of the very concept of optimal paths in rare events. And now I switch to the main topic of the talk, which is symmetry breaking. And again, symmetry breaking is something that we are familiar with from our very childhood. And some of us have seen it with our children, and some of us could have seen it with our grandchildren. So here is what it is about. Suppose formally you have an oscillator, an inertial term, friction term, eigenfrequency, and you modulate the eigenfrequency periodically. In time, now you need to have nonlinearity, and this nonlinearity is the leading order term. Don't ask me why there is no q squared. Say that the system has inversion symmetry and there is no q squared term. If I have q squared, it doesn't change anything. The model is swings. And so think that you are on swings and you start vibrating on swings. So what you are doing, you are squatting up and down. And let's count it. I squat, I go forward, 1 forward, 1 backward. So 2 backward, 3 forward, 4 backward, 5 forward, all odd forward, all even backward. This is one scenario. The other scenario is that 1, I go backward, 2 forward, 3 backward, 4 forward. The other scenario is when I shifted in phase by pi. And these two scenarios are totally equivalent. There is no difference. And this is what is called period doubling in mechanics, because the vibrations, the period of the vibrations on swings is twice the period of squatting. Again, I do 2 squats per vibration period. So this period doubling is essentially a signature of broken time translation symmetry. I have imposed time symmetry by squatting. Now I have broken it. My system has broken it because it is a nonlinear system, and this is what is called parametric resonance. Okay, has been known for probably like a few thousand years. New life started with the paper by Wilczek. This is a Nobel laureate, which is one of the godfathers of the standard model in physics. He published a paper which was called Quantum Time Crystals, Classical Quantum Crystals and Quantum Time Crystals back to back in parallel. In 2012, three years later, there was a paper which is called Absence of Quantum Time Crystals, which showed that Wilczek actually was wrong. There are no time crystals in equilibrium systems. And this is good because, as you understand, there would be no energy conservation if time were not uniform. So fortunately, there are no time crystals. Well, then, a few years later, there was a couple of theory papers that described broken time translation symmetry in driven systems, and then experiments that actually showed that, yes, in a driven system, you can have broken symmetry. If the system is not driven and you had broken time translation symmetry, this would mean no, but think about it. The energy would not be conserved because energy conservation is a consequence of time translation invariance. It's the ground state that breaks time translation symmetry. And of course, it's continuous symmetry. If you break it, there is no energy conservation. So there is no, it's clearly internally controversial statement. Ground state means the state with minimal energy. But if the energy is not conserved, what are you talking about? So this was kind of trivial, and therefore I was quite annoyed by this paper when I saw it in the archive. Anyway, then there was an experiment on driven systems, and again, this is very similar to what I talked about when I was talking about a parametric oscillator. But of course, in all magazines, there were claims about new state of matter that has been discovered. Then I looked more carefully. It turns out that in all these pseudoscientific publications, new state of matter is discovered roughly at the speed of one new state per month. So, so it's not that dramatic. But back to our parametric oscillator. So I told you that because there is noise in the system, there are fluctuations, the oscillator can switch between these period 2 states. And of course, if there is switching between the states, that on the long time scale, this symmetry, time translation symmetry, is restored. And indeed, there was a theory of the switching rate, and there was this experiment actually with this electron in a cavity, which was done to observe these transitions and study it. And since then, there were experiments in other types of these mesoscopic vibrational systems with optically trapped atoms, micromechanical oscillators, superconducting microwave cavities, and so on and so forth. So there are quite a few vibrational systems. And what I want to do now, I want to tell you what happens when you couple several vibrational systems and how this interaction between the vibrational systems leads to a new behavior of, in the presence of a drive. So let's start first back to one oscillator, which is periodically driven. I start with the Hamiltonian, and the Hamiltonian has momentum, has frequency, which is periodically modulated, and has the nonlinear term. And I choose the frequency of the drive being approximately twice the eigenfrequency. This is what you do if you want to have parametric resonance. And to describe this dynamics, I changed to what is called the rotating frame. I don't know if you can see it, but essentially the motion consists of vibrations that you excite. And the amplitude and phase of these vibrations change comparatively slowly. Therefore, I want to separate these fast vibrations from the amplitude and phase, and I change to the rotating frame. Rotating because essentially Q and P are, I change to new variables capital Q and capital P, and the angle is, it's a rotation. It's just standard rotation, but the angle is proportional to time. And then after that, I can disregard fast oscillating terms in the Hamiltonian. I make this canonical transformation, and the Hamiltonian becomes, in new variables, it becomes independent of time. So Q and P are coordinate and momentum in this rotating frame. What is important is that this Hamiltonian is not a sum of the kinetic and potential energy. It's kind of, if you like, relativistic term, Q squared plus P squared. This is what you get. What you get if you take, for example, an electron and magnetic field and allow for relativistic effects. So this is not a sum of the kinetic and potential energy. And this is the surface that I showed before. It's this Hamiltonian as a function of coordinate and momentum in the rotating frame. If I make a cross-section of this surface by the plane where this momentum is equal to 0, I have a double well structure. And if I take into account dissipation, weak dissipation, then this minima becomes stable state. Now I don't want to describe dissipation phenomenologically. I can do it phenomenologically, or I can do it microscopically, and then I get Markovian dynamics in this slow time, slow compared to the vibration period. So I want to emphasize that this is not an approximation of the density of states of the thermal reservoir. This is just an approximation of slow time. In slow time compared to the vibration frequency, my oscillator just is seeing the thermal reservoir around it only in a narrow frequency range. And if this thermal reservoir doesn't have any singularity in the density of states, then the vibration, then the dynamics becomes Markovian in this slow time. So I have then this equation. The first term is just the Hamiltonian dynamics, right? It's dPg and dQg, the Hamiltonian term. The second part is decay, and these two terms, Fq and Fp, are noises, and these noises in the classical description are just independent Markovian white noises. In the quantum description, and this is what makes quantum problem more interesting, they do not commute. And it is more or less clear why they cannot possibly commute, because you have to preserve the commutation relation. And if you don't, if they were commuting, there would be no commutation relation. But I will be talking about classical theory today. So I have this stochastic dynamics. I can talk about the behavior of this system. I go back to this slide that I showed before. I have the dynamics where R is just a two vector with one component is Q, the other component is P. I have this equation of motion that I showed before. I can calculate the switching rate, and the switching rate is just e to the minus some function R over D, and this function R is the minimum of this functional, as I showed at the beginning. And this is actually what was used to calculate this plot that I showed before. And the experiment was done by Chan at that time in the University of Florida. Now I want to couple these oscillators with each other. So I have these oscillators somehow coupled. It can be one-dimensional chain of oscillator. It can be two-dimensional chain of oscillator. I don't know how to make a three-dimensional chain, but probably it can be made. Hasn't been so far. And the result that I will be talking about have been obtained with Christoph Brudel, Niels Lurch, and Yaxing Zhang, and are on the archive. So we'll start with the Hamiltonian, which now is the Hamiltonian of these individual oscillators. Each of these nodes is an oscillator. And the Hamiltonian of coupling. And I take the simplest form of coupling. Actually, the results are not very sensitive to the particular form of the coupling. I just take a harmonic coupling in the displacement of the coordinates in the laboratory frame. If I go to the rotating frame again, then this first term is just the sum of the Hamiltonians of individual oscillators in the rotating frame. And the second term is the sum, now it becomes QP plus PP term. This is just the price of rotating. Not a big deal. Back to the problem of switching. So if what I will do now, I will use subscript sigma 1 and 2, which enumerates the states. For example, 1 is the left state, 2 is the right state. Or minus 1, excuse me. What am I saying? Yes. Sigma is not 1 and 2. I'm sorry. Sigma is minus 1 and 1. It's spin. So minus 1 is the left. Minus 1 is the left well, or plus 1 is the right well. Now let's talk for a second what will happen if I have two uncoupled oscillators. So I just have two uncoupled oscillators. One of them can have this phase. The other can have another phase. Or that is, one of them can be in this minimum of its energy in the rotating frame. The other can be in another minimum. And the probabilities are equal. So on average, I don't have any order in the system. The symmetry is preserved. And of course, the rates of switching from left to right and from right to left are the same for the oscillators because it's just individual oscillators. The rates are the same. Now I want to couple them. And let's start with a cartoon. Let's assume that I keep one of the oscillator in one of the minima. Then I couple it to another oscillator. It essentially tilts the energy. Now you have to keep in mind that this is a cartoon, that what happens in reality, that this oscillator is oscillating. And when I say that it is in this well, it means that it is oscillating with this phase, with the blue phase. And if it is in this well, it is oscillating with the red phase. So, but again, this is also oscillating. And essentially, this is about synchronizing these oscillations. These oscillations, when the phase of this oscillator corresponds to the blue line, the phase of this oscillator becomes deeper G for example, also blue line for this oscillator, and more shallow for this oscillator. So it's essentially a projector on the rotating frame, and I'm talking about weak coupling, so if this oscillator is in this well, the symmetry for this oscillator is broken. And again, naively, you can think that you have an activation switching. Activated switching, it's like Kramer's rate. I don't know if these words are familiar. Do you know, is this term familiar for switching between the minima of Brownian particle in a potential well? Activation over the barrier, more or less. Right. So I tilt it, and of course, the rate of switching from a shallower well should be larger than from the deeper well, naively at least. Well, will it be or will it not be? It has to be calculated. And essentially what I have to do, in reality, I have to say, OK, I have my system. I have my equation of motion, which now has these full equations for nth oscillator with full energy, with decay and random force on each oscillator. And now I have to calculate the switching rate for an nth oscillator, from switching from -1 to 1, and from switching to 1 to -1. So I change the notation, W sigma corresponds to switching from the well sigma. And R sigma n is the activation energy, quote unquote, for switching from the well sigma to the well minus sigma. Now, this switching, again following that same optimal path terminology, is given by the minimum of this terrible functional. What I notice here is that the force on the mth oscillator has two terms. One term is if the oscillator was isolated, and the second term comes from the coupling to other oscillators. So this delta Kn is the term which corresponds to the interaction part of the energy, and I use curly brackets for Poisson brackets. So these are Poisson brackets. This is just Hamiltonian dynamics. Now, the good thing about this calculation is that if I want to consider the case of weak interaction between the oscillators, I can calculate this change of the activation energy by perturbation theory, calculating just the integral of this part delta K, which comes from the coupling, along the unperturbed trajectory. This is the key element. This is what allows you to do the calculation. So it's just a property of Lagrangian and the least action principle, if you like. And so I know how to calculate, and I do this calculation. And what I get is the following. Let me write this expression for delta K explicitly. So it has a term which corresponds, which is determined by the value of m for n oscillator. This term has components that are determined by the momentum m of the mth oscillator and coordinate of the mth oscillator. And since I am talking about perturbation theory, I can use for these values the values that correspond to the stable state. Physically, the picture is the following. I have my coupled oscillators, and if one oscillator switches, most likely all other oscillators are in their stable states, because it's very unlikely that two oscillators will switch at a time, two coupled oscillators. If the coupling is short range, if the coupling is long range, it's a different problem, and I don't know the answer. But if the coupling is short range, it is clear that if one oscillator switches, other oscillators stay where they are. And therefore, I can say that I can use for these terms just their equilibrium positions. And these equilibrium positions have opposite signs in these two equilibria, which I describe by parameter sigma. And therefore, my delta R, my change of the activation energy for switching for nth oscillator from state sigma, it has opposite sign depending on which well I am switching off. So it is proportional to sigma n. And it is given by the term sigma m, sum over m, for different oscillators which are coupled to the oscillator that I am talking about. So I have this picture of delta Rn sigma, which maps my problem on the following. So my switching rate now becomes the switching rate in the absence of coupling, and the terms which is painfully familiar for the Ising model. Essentially, I map the system onto the Ising model with a big caveat. This is a non-equilibrium system. There is no detailed balance in this system. And therefore, generally, J and M is not equal to J and M. So it becomes an Ising system if all oscillators are identical. If the oscillators are not identical, it's not an Ising system, and there is no detailed balance. What I know about the Ising system is, of course, that I can have all kinds, just the standard Ising transition in my system. And this Ising transition in the system of coupled oscillators is now happening in the time domain. So the system of oscillators in the ordered Ising phase corresponds to all oscillators vibrating in phase, certain phase. And this is what makes it interesting. So if the coupling is ferromagnetic in the Ising model, then they all vibrate in phase. If the coupling is anti-ferromagnetic in the Ising language, it's just the sign of this coupling parameters, there can be anti-ferromagnetic system, you can have frustration, you can have all the beauty of the Ising system, you can have dimension of the system that you like, you can have a chain, you can have 2D, and maybe you can have 3D, I don't know.
Stable when you go beyond the weak noise limit?
Well, if the noise is strong, then of course you melt your Ising system. It's just noise plays the role of temperature.
No, but what I'm asking, if you do the first correction to WKB approximation.
It's just the prefactor, doesn't change anything. No. The first correction doesn't change anything. What is important is, of course, that this term beats against the noise intensity as in standard Ising model. So if noise becomes strong, then I don't have an ordered phase.
Here it must be weak compared to the coupling.
To the coupling, right.
So it must be really weak.
Right, it must be weak. It must be weak. Well, it's not very critical. I will talk about it, yes.
The system here is infinite, right? Otherwise,
Right, of course.
this will kill it.
Right, of course. So, so what happens now, the funny behavior happens when I start approaching what is called the bifurcation point, and Ira was talking about it on the first day, the point where the system is close to the onset of these periods to vibrations. And as you know, on swings, you have to squat sufficiently strongly, otherwise you will not start vibrating, right? So when you are close to this bifurcation point, there is always a slow mode. It's like soft mode in phase transitions. One variable of the oscillator becomes slow in time again. And then the equation of motion is very much simplified. It has this simple form of motion in a potential for this mode, and this potential has a simple form of double well potential. For a soft mode, think of the Landau potential. Right? So this is exactly it. Again, what is interesting is that the coupling effectively becomes stronger because the coupling is scaled by the distance to the bifurcation point. So you start approaching the bifurcation point, the system becomes softer, and the coupling, of course, becomes effectively stronger. So this is the behavior that you can have. The other kind of behavior which emerges here is when the coupling is no longer weak. If you are close to the bifurcation point and the coupling is no longer weak, then your whole system is projected on the coupled Brownian particles, overdamped, which are moving in some potential landscape. And in this potential landscape, you can have, of course, many metastable states. Each of them has broken time translation symmetry. And the system fluctuates, so they can switch ultimately between these states, so you have some kind of a glassy behavior. This is what happens with essentially this simple system. And now, for the last 2 minutes, I will talk about what has been seen in the experiment. Yeah.
Comment about the dimensionality. I mean, clearly in one dimension this will not happen, right?
Right.
So what is?
Well, it's think about a potential landscape, for example, two-dimensional potential landscape, and you have Brownian particles which are coupled and are fluctuating in this two-dimensional.
So 2 dimension is enough.
Yeah, I think so. Yeah, I think so. For having metastable states, clearly, yes, it is enough. Yeah. No. I'm talking here about metastable states. I'm not talking about the ground state. I'm talking about metastable states. But these are many-body metastable states, so they live long time. And each of them has a broken time translation symmetry. So this is what was interesting to me, that you have these metastable broken symmetry states. In contrast to the standard picture, each of these states has broken time translation symmetry. So the experiment was done with optically trapped atoms, and this is actually a slightly different picture from what am I talking about, and it was done, interestingly, about 7 years before Wilczek's paper. And it was not claimed that this is a new state of matter. So that was the problem with this experiment. So you have optically trapped atoms, and you start parametrically excite vibrations of these atoms. This is done in the experiment. It's called atoms, and you just modulate the intensity of the lasers that confine this atomic cloud. And if you start this modulation and it's sufficiently strong, your intensity is periodically modulated in time. What happens is exactly what I was talking about before. If the density of these atoms is small, you have some of them vibrating with one phase, and some of them vibrating with a different phase. And therefore, you have two clouds which just vibrate in opposite phase with each other, two independent oscillators. Now, what happens? What is the physics of it? So the interaction between individual atoms is very weak. The distance between the atoms is big. It's low density. It's a low density cloud. And what can happen is that atoms can switch between the clouds, but then switch one by one, essentially, one atom at a time. What happens now, because there are atoms inside the clouds, they shield the switching atom from the light. So this is the mechanism of the interaction, what people in cold atom business call shadow effect. This cloud provides a shadow which shields this atom from the modulating light, and therefore this changes the probability of switching. Now, what is important here is that this shadow effect depends on how many atoms are in this cloud and how many atoms are in this cloud. So it is instantly the mean field picture, because it's a collective picture. This atom is seeing the total number of atoms here and the total number of atoms here. This is what changes the switching rate. And therefore, the switching rate is essentially proportional to the exponential of the difference of the populations in the two clouds. And these populations in the two clouds are now the new collective variables. They are slowly variable because they are slow variables because they change because of the switching, and switching rate is small. And you can essentially map this problem on the mean field Ising model. Mean field because you just have two variables: the total number of atoms with one phase, and total number of atoms with the other phase. And this is what they observe: that when the total number of atoms in the both clouds is less than critical, you have two clouds which oscillate in counterphase. But as you increase the total number of atoms and you increase effectively the coupling between the clouds, these two clouds collide and you have spontaneously broken phase. So this spontaneously broken phase and this whole transition is of course just a mean field Ising transition. And they have measured the exponents. So the theory is pretty straightforward, and again, it's cold atoms. You don't have parameters. You calculate things. You calculate the switching rate. You calculate how it is modulated. You find this parameter alpha. You find everything. You find the critical total number of atoms in the clouds, and you calculate the mean field behavior. So the order parameter is the difference between the populations of the clouds, and this difference, of course, has a square root dependence on the critical value. You look at the variance, and it has the proper power law behavior near the critical point. You look at the response to a trial field susceptibility. It has this 1/3 exponent, so everything works just fine. And just one word on quantum theory. I did not talk about quantum effects, but everything that I talked about here extends directly to the quantum theory, except that if you are in the coherent regime in the quantum theory, you have a quantum phase transition. You look at the energy spectrum, at the spectrum of the excitations of the system, and this spectrum is gapped when you are above a critical phase transition point. It's linear at the critical point, and again gapped built in the symmetry broken phase. So you have a real symmetry breaking transition, quantum phase transition in time. And with this, thank you very much.
Thank you. Questions? Yes?
Sure. So these are infinitely coupled systems, for example.
Yeah.
Yeah. So normally, if you have finite effects, so large numbers, but they're finite, you allude to one that switches while the others stay
In the
stable
right.
equilibrium,
Mm-hmm.
So my question is, when you look at the laboratory, in the rotating frame, right, where you don't have time explicitly, so it's removed, you have autonomous systems, and so you can see some of these shedding effects with finite systems, and it's not universal. So if I change my architecture that couples the system, then you get different results in terms of scaling.
In the mean field picture, it's of course irrelevant. But in the real system, of course, I have different connectivity in this. I can engineer the connectivity as I like. This picture actually shows the connectivity in the case of microwave cavities. So this is a two-dimensional lattice ordered of coupled modes in microwave cavities. This has been done. And depending on the connectivity, of course, I will have different. It's not a true phase transition, of course, in a finite system. But still, the symmetry will be broken for the time which is much longer than my lifetime, that's for sure.
Other questions? Well, if not, let's thank the speaker again and go for lunch.
Thank you very much, David, for inviting me. Okay, so today I will talk about the Kardar-Parisi-Zhang equation. Okay, and there are big experts in the audience, but there are also people that maybe are not used with this model. So I will start with a review, but I will focus. I mean, the most recent subject is about the large deviation, the very rare events in the Kardar-Parisi-Zhang equation. And in particular, I will talk about a recent work that we did with Alexander Hartmann that was visiting us last year. And so it's based on the fact that we can actually observe these very rare events using this important sampling technique. Okay. So there are different, I have to say, that the others are my colleagues in my lab in Paris, so Satya and Gregory, who was here, and Pierre Ledoussal, who is in the École Normale. And so there are different models in which that belong to this universality class of Skardar-Parisi-Zhang. The first one is the interface, which fluctuates by with thermal noise with a nonlinear term. But the other important model, at least one of the three important models, is this directed polymer with random media. So I come from disordered system. This is an equilibrium problem. And the idea is to find an optimal solution in a very complicated disordered landscape. So imagine that you have this two-dimensional lattice, and you grow a polymer. So it's called directed because there are two directions. One is the spatial direction, and the other is called the time direction, in the sense that the polymer is obliged at each time step to grow of a unit. So you cannot have loops like this, okay? And at each time step, the polymer has two possibilities. Either it go right, either it go left. And you construct a configuration like this blue configuration. And because every time you have two possibilities, if you consider a polymer of length t, you will have 2 power t configuration in this lattice. And the random media is due to the fact that each site on this lattice is associated with a random number that can be Gaussian, exponential, or uniformly distributed. And at each configuration, you associate an energy. So the energy of the polymer will be the sum of these t random variables. And the game is to find the best one, so the one which minimizes the energy. Okay, so you have 2 power t possibilities. And the energy which minimizes this sum of random variable is, has the same universal behavior as the 8 of the KPZ interface. We will see this in a second. So first of all, is it difficult to find this minimal energy? Because you have 2 power t configuration, so you can imagine that is an exponential problem. You have to enumerate all the 2 power t configuration, compute the energy, and find the minimal one. If this is the algorithm you use, then you understand that you can do maybe 12, 15 polymer, length 12 or 15, but you cannot reach very large sizes. But actually, I don't know what, okay, here. Actually, we are lucky because in '59 there was this computer scientist, Dijkstra, that found an algorithm that is able to find the best path very easily. And actually, this algorithm is the same algorithm that constructs with Google Maps the best itinerary. So if you want to go from Paris to Novosibirsk, in few seconds you have the answer and you don't have to wait a huge time. And the same if you want to find the best path for the polymer, is something that arrives very quickly, okay? And so this algorithm is very famous and has a lot of application, even if this person was a very successful scientist but didn't get any penny because of this algorithm, okay? And so how it works? So the idea is very simple. So you want to, instead of enumerate all the configuration, you want to evaluate the energy that the minimal energy that you need to arrive from the origin to this point in red. So it's a recursive algorithm. And what this algorithm tells you is that this energy will be the energy of the impurity sitting here, plus the minimal energy between the 2 energy that you need to arrive at this point and at this point. So if you are able to solve the problem at time t-1, then the solution at time t, it will be just given by this recurrence relation, okay? So the naive algorithm was 2 power t configuration. This algorithm is the number of recurrence relation that you write is exactly equal to the number of sites that you have on this lattice, and so it grows with t squared. So it's polynomial in t squared instead of being exponential. So it's a problem that is very simple to treat. And so you can now reach polymer which are very, very high. Ah,
Just I have to understand this. Let's say Vx of t in the next step is infinity, right?
yes.
You have to reformulate all your previous history to redirect yourself to a new point.
So V is the energy of your impurity.
The next step.
So you are here, you want to go here, you want to go from here to here. You know what is the cost to arrive here and what is the cost to arrive here. So the cost to arrive here, it will be the impurity you have in the blue point plus the minimum between the two costs. Locally, you decide if you come from left or right.
But we need to consider still all the paths, no? Because if that point is the last point is has infinite energy,
You need
to reconsider everything.
No. You need to construct a path for each final destination. Not all the path, but all the final destinations. So you have t-square destination. The paths are much... So you have t-square impurity if you want, but you can construct a 2 power t path. And the algorithm grows like the number of sides of impurities and not like the number of paths. Okay? It grows like the dimension of your system, not like the number of paths. Okay, so now let's go back to KPZ. And so now I will discuss results for this boundary condition. It's called the droplet. It will be clear why it's called the droplet later. So you start the polymer at the origin and you want to go back at the origin in t steps. All the possible paths have exactly t steps. And so you can do this minimization, let's say, for 10,000 samples, and then you average the energy, and it is quite clear that this energy will grow with the size of your polymer. It will grow linearly, because it's an extensive quantity, as the size of your polymer. The prefactor is non-universal. If you change your distribution of the disorder from Gaussian to uniform, we'll have another value and nobody is able to predict it. But what is universal are the fluctuation from one sample to the other. So if you look at the standard deviation, for example, of the energy, this has a universal property. So it is tradition to define this variable H0, I mean at zero temperature, and you take the average energy, you subtract the energy of your sample, and this variable H0 has many universal properties. So let's see the first one, the one was found in the 80s, okay, is that if you look at very large polymers, the fluctuations of the energy grows not linearly, but like t power 1/3. And this is very non-trivial because you are summing random variables. So you can imagine that the fluctuation scales like square root of t because of the central limit theorem. If you take two polymers without any optimization, the difference in energy will be square root of t. The fact that it grows like t power 1/3 is because of the optimization. And then a little bit later, Joachim and collaborators, they realized that this is not the only universal quantity. There are not only critical exponents that are universal, but the full distribution actually is universal. So if you look at the full distribution with the droplet boundary condition for system of large sizes, and you look at the kurtosis of the skewness, and you change the distribution disorder from Gaussian to uniform to exponential, the distribution is exactly the same, okay? And what is this distribution? This was found much later, 10 years later, and people realized that this distribution of H0 is exactly the same distribution of the largest eigenvalue of a random matrix. And depending on the boundary condition that you put, if you use a droplet boundary condition, it will be the GUE Gaussian ensemble, beta equal 2 for the Dyson matrix. So for people that doesn't know, the random matrix has different classes depending on the symmetry of the random matrix, and there are different Tracy-Widom distribution for the largest eigenvalue. Okay? For GUE, it's called F2, And all this family has the same feature when you look at the very extreme, events. So if you look at energy which are very large, when H0 is very small, then it decays in a non-Gaussian way with the power z cube. All, yes, absolute value of z cube. So it decays very fast to 0, much more than the Gaussian. While on the positive side, for energy which are very small, because I took minus AT, it decays much less than a Gaussian with a power z 3 by 2. Then if you change boundary condition, this will change 1/12 and 4/3, but will not change these two exponents. Okay, they are strong and the characteristic of all random matrices. Okay, and also of the KPZ universality class.
Between E and H naught.
Yes, so is this one. So you take the extensive part and you put minus E. So why you do that? Because usually people talk about the maximum of the, in random matrix, you look at the maximal eigenvalue. If you put E minus the average, it will be the minimal eigenvalue, but it's more natural to describe things like that, okay? So it's the only, so when I will talk about the right tail, it will means, the right tail is this one, it will means very small energy, and left tail is very large energy, okay? So now this is about the typical fluctuation. So I said the fluctuation grows like t power 1/3, they are absolutely non-Gaussian, and they have these two tails, left and right tail, okay? Now, you can ask for very rare events, okay? You can ask for events which are not of the order of t power 1/3, but for example, you can ask, I have a long polymer, what is the probability that the energy is the double with respect to the average energy? Or is the half with respect to the average energy? And so these are very rare events, so you should use the large deviation approach. And so Satya, Pierre, and Gregory, they propose something which also has a correspondence in random matrix, is that the probability to find a very small energy should go like exponential minus t, so is exponentially suppressed in time, times a non-trivial function phi plus. And on the other side, if you want to know what is the probability to find an energy which is the double with respect to the mean, it is much more suppressed, and is suppressed with t squared. And this is simple to understand, because imagine you want to find an energy which is half of the optimal energy. What do you need? You need to find a path where the impurity along the path are very small compared to the typical one. So this is a rare event to have one of such impurity, which occurs with some probability p, and you need t of them in order to have the path. So you need a deep valley in a typical landscape, and this deep valley has length t, and so this is the reason of this factor t. Now, if you want to find a minimal energy, which is the double of the typical one, then you don't need just a path which is very costly, because otherwise you will avoid it. You need that the full space, full two-dimensional space, is covered by very rare impurity, which are very high, okay? And so because it's a space that scales with t squared, this is the reason why it is exponentially suppressed with t squared instead of t, okay? So this is the time to make a point. So what we have seen is that no matter which distribution you use, you will find features which are common to all the models. The first one, which was the most famous, is this exponent 1/3, okay, that comes from the optimization for the standard deviation at long time. Always at long time, you know that the fluctuations are fully universal with this Ricci-Widom distribution. And then you know that there is this scaling form for the large deviation. But there are many things that you don't know. For example, you don't know the statistics of a short polymer. You don't know of a medium polymer. You don't know the standard deviation or the prefactor of the standard deviation or the prefactor of the mean energy. These are non-universal quantity. And also is non-universal these two functions. If you change the distribution of the disorder, you will have different functions. Okay? So one thing that people can do is that few models in the KPZ universality class can be actually exactly solved. So they are integrable. Okay? And between these models, there are models on the lattice. But there is one model which is more important than the others, is the continuum model. So really the KPZ equation that you write on the blackboard. And this model, when you have a lattice model, you can also simulate, for example, in a limit in which you recover the behavior of the continuum model. And for this model is the high temperature limit. So if you heat up, if you add the temperature, instead of looking at the ground state energy, you look at the free energy of the system. When the temperature is high enough, this discrete model will have features that are independent of many things and will be the one of the continuum model. In particular, first of all, you have to generalize the Dijkstra algorithm with temperature. So the recurrence relation is now not for the free energy, but for the partition function. So the weight of all paths that arrive here is equal to the sum of the two weights to arrive here and here times the Boltzmann factor of the new impurity. And once the difficulty is the same, once you have the partition function, you take the log and you have the free energy, okay? And so all the details of your discrete model, when you go to the high temperature, they go inside of these three constants. The temperature, which is the one you put, the elastic constant of this continuous elastic line, that for the model I've used on the lattice is equal to 4 times the temperature. For other model, it will be different. And then the strength of the disorder. Now the disorder becomes a white noise, and C is the strength, the variance of your impurity. And why is like that? It's quite easy to understand why, because there is a kind of hand-waving reason, is that when you hit the system, at short scale, the polymer starts to vibrate, okay, and will explore all the impurity around. And so you are kind of summing these impurities, and you recover a kind of central limit theorem that gives you, that transform your noise, the distribution of your noise, in a white noise case. And this model is actually integrable. And this is the partition function that you write in field theory. And then you can associate a Schrödinger equation to this path integral representation, which is given by the Feynman-Katz. The Schrödinger equation for the partition function is a diffusion equation with a multiplicative noise. And there is a Kolopf transformation, that is this one. So you associate the log of z is the 8th of your KPZ equation. And then the 3 parameters are linked in this way. And if you do these 2 steps, you will arrive to the continuous KPZ equation. So this is the equation for an interface, which is the free energy of our model. This is the diffusive term. This is the famous nonlinear term of the KPZ equation. And this is the white noise, the thermal noise of your temperature. Okay, you don't need to do that, but you have just to believe me that when you study the model at high temperature, the results are really the one given by this model, by the continuum KPZ equation. And then, so what you have to do in practice is that now is not H naught, because we are at finite temperature. You have a new variable that is universal and now is also integrable. So everything is known about this variable, and is just log of z minus the average value of log of z. And the important point is that the length of the time of your, if you want, of your KPZ equation is rescaled in this way. So you take the length of the polymer and you divide it by the temperature power 4. So it means if you are at high temperature, that you have access numerically at the short time behavior. Okay? And so what you discover is the fluctuation of H are exactly the same fluctuation of this experiment of Takeuchi, okay, where he grows this droplet of turbulent fluids, and this is the H field of his droplet, and the fluctuation of this H field are exactly the fluctuation of the free energy of this polymer with this droplet boundary condition. Okay. So in practice, what you do when you when you integrate this model is that you compute the moments of this partition function. So this is the thing that you can do explicitly, okay? And once you have this explicit solution, for example, this is the second moment of the partition function, you can find, for example, a short time expansion of the fluctuation of the free energy. So let's go back a little bit just to understand. So you have this equation, okay? We are at high temperature, so nu is very large, and you look at short time. So if nu is very large, you can neglect this term at short time, and this becomes a very simple equation because now it's linear in H, is the Edward-Wilkinson equation, and H has Gaussian fluctuations. So when you look at short time, you see a Gaussian term plus correction that comes perturbatively in lambda due to the nonlinearity. And so this is what you see here. This is the variance of the Gaussian fluctuation, and then you have subleading correction, okay, that comes from the cumulants, high-order cumulants. And again, here there is no adjustable parameters, okay? So these are the simulation of the lattice, and this is in the straight line are the prediction of the Bethe-Ansatz solution, okay? So actually, we are able to write an exact generating function for the full distribution of the free energy. It's defined like this, okay? The generating function. And you have to sum all the moments of the partition function. The problem is this is an important result in the field, but so this is the full expression of this generating function Q for this droplet initial condition. The problem is that this Fredholm, so is an expression that is in some sense formal, in the sense you cannot plot it, you can look it, okay, like any cone, but it's not something useful, okay, and then you have to understand how it behaves in order to really understand the statistics of the interface, okay? And so it was found by many people, and what we did is to find using the directed polymer, while these people use another model, the weakly asymmetric exclusion process, okay, which is also in the Kardar-Parisi universality class. So now, the more recent result concern these very rare events. So what I was telling you before, okay? And now we can characterize them not only at long time as all the universal results of KPZ, but also in this short time behavior where the nonlinearity start to become important, but is dominated by the Gaussian fluctuations. And so what we were able to do with Pierre, Satya, and Gregory was to write an exact expression for the short time behavior, which is, this is a special function, but is a simple function. And so it's not anymore a Fredholm determinant. And when you use this generating function to write the full probability to have a probability density function for the variable H, you have a form which is quite simple and which is plotted here, is this black function. So here I plot two functions. The blue one, or the violet one, is the Gaussian distribution. So if you look at fluctuation around 0, you find that the distribution is Gaussian. But when you go far away, the distribution is very different from Gaussian. And actually, it has tails that was first predicted by Baruch. There are two tails. So if you look at very high energy, or very high free energy, you find exactly the same tail of Tracy-Widom. So we are at short time, but you see you have 4/3 H 3/2, which was exactly the same tail that you will have on the Tracy-Widom distribution. While there is a new tail, okay, which was very interesting, which has another exponent. It's not 3, but it's 5/2. Okay, so a short time, there are non-Gaussian correction due to the nonlinearity. This one is exactly the same as Tracy-Whedon, while this one is a new one. And now, and here we arrive to one of the points I want to make, is, okay, we have this rare events statistics, and we can have two questions. The first one is, is possible to observe such rare event, or is something that is just nice to have on the books, but is impossible to see, okay? And the second one are relevant for applications. Okay, let me first answer to the first question. Is possible to see, to draw this, to do a numerical simulation and observe this very rare sample that have extremely large energy or extremely small energy? And the first answer is no, because what you can do is the following thing. You can generate your disorder configuration with your probability, Gaussian, exponential, or uniform, and then you can count. So let's say that our observer is the probability to observe a configuration which h smaller than -30. Okay, the typical value is 0, and now we ask what is the probability that h is smaller than -30. So you can generate n-trials configuration, okay, and count how many times you have h smaller than -30, okay? So your observable, O, it will be 1 when it occurs and 0 when it doesn't occur, okay? And so, because we have a very, very good algorithm, we can arrive up to 1 million, typically. You can do 1 million of polymers. And so with 1 million of polymers, you can estimate numbers that are of the order of 10 minus 6, because you have one successful realization against 1 million. But you can never measure number of this kind, okay? You can never measure, if you go and see what is phi drop here, so to be smaller than this value, it will be to have an event that has a probability 10 minus 153, which means that you need this number of samples, which is completely impossible to have. So you need to change technique. You don't have to do this naive thing. You have to use a technique which was invented by Ulam a long time ago, and is called importance sampling, okay? Actually, the problem that you have is that your observable is either 1 and either 0. And summing this number, you want to do 10 minus 153, which is very difficult, okay? What you would like to have is that it's very likely to find the sample of smaller than -30, but the observable in this case should be smaller, should be of this order of magnitude. And summing numbers of this kind, you will have a high precision on that, no? And so to do this, you have to change the distribution with which you generate the disorder. So you multiply divided by a new distribution p tilde, and if you are strong enough and you find a p tilde that gives you many configurations with an energy smaller than -30, then you are done. But the price to pay is that the observable is now the old one, which is 1 or 0, times this ratio, okay? And so in the importance sampling, what you usually propose is the exponential tilt. So you say, I will adopt the same distribution as before, but I will give an hour to the guys that have a very small energy. So you multiply by exponential minus theta h that you measure, okay? And theta is a kind of temperature. If h is -30 and theta is positive, it means that this distribution proposes much more likely distribution configuration with a very small h. And now the observable will be exponentially small, okay? And when you have, so now the question is how to produce this p tilde, and there is always a way. You have to use Metropolis, and it's something that can be painful to do. So it's easy to say, it's less easy to do, but you can, given any distribution, you can also always sample it using your Markov chain Monte Carlo that bring you to this rare, strange configuration that are very unlikely. And thanks to this easy equality, everything is exact. And so just to give you a flavor of the difference, here I did the standard Monte Carlo with 1 million of samples. So you see The black line here is the exact distribution. The pink line is the Gaussian guess, and the numerical simulation are the red dots. So you see that they are moving to black, but you don't see the tails, okay? And now this is the important sampling distribution. So you go from 10 minus 6 to 10 minus 800, okay? So here there are the numerical data, are these lines, okay, for different lengths of the polymer. So the continuum limit becomes more and more exact the bigger polymer you have. Then you change the temperament in order to fix the parameter T at 1/16. And so you see that there is a perfect agreement, and you can explore well the two tails. So I have a figure for that. So this is the right tail. So this is the Tracy-Widom tail 3/2. And this is the new tail, the left tail, that is perfectly matching. So these are the numerical simulation. This is the tail, and this is the exact result. Okay? No, sorry, the theory, and the exact result is the line.
How do you take care of, there's always a problem with these things that the normalization?
You match, very good point. So yes, let me go back to this. So let me go back to this. So here it is clear that if you have a positive temperature, theta positive, you will go to H very negative. But if you want to do the full distribution, then you have to do another simulation with theta positive, and then you will have H very large, okay? And then you will have piece of the distribution, okay? For theta equal to 0, you find this one. Then you take a theta positive, you will have a piece like this, and you just glue them. This is the way, so this simulation glues different simulation, okay? Because his point is that when you have a piece like this, it's difficult to normalize, okay? Because it's in a region where the contribution to the normalization is almost 0. But here, the normalization, you take the one in the central part, okay? Okay, so I was here. So the tail of the short time are well verified, okay? And now the other point is to look now at long time. And here there was the scaling proposition by Satya and Pierre and Gregory. And so what they propose is in the middle, we will have that now is not Gaussian. We have the Tracy-Widom distribution, and we have to match this Tracy-Widom distribution with a left tail and the right tail that should be determined. And so what they were able to do was to determine the right tail. And again, is always the same. The right tail is always the same, is this 4/3 Z 3/2, okay, power 3/2. Now, Baruch came back again. So he found, with Prolak and Sasorov, he found an impressive result. He found the left tail, okay, is this expression, the full expression of the left tail. And you see that when the parameter is small, so when you approach Tracy-Widom, it perfectly matches with the Z cube. But on the opposite direction, when H is very, very small, then you have the tail 5/2 that you have also for the short time behavior. So, as I said, it's very difficult for the numerical simulation to access in the continuum limit at the long time behavior, because this time is the length of the polymer divided T⁴, the temperature power 4. So we were able to arrive to this length, 32, which is not extremely large, okay? And so you should see first this figure, okay? So these are the numerical data. The dots here are the numerical data T = 32. This is the right tail. So this is the Tracy-Widom right tail. You see that it works very well with the data. And then you reach the bulk. Here is the zoom on the bulk. So this is the Tracy-Widom result. And this is the Tracy-Widom result. And this is the results of the numerical simulation. So they match well. But then on the left tail, there is a disagreement. And if we use now the results of Baruch, so here is a blow up of the left tail of this part, okay? You see that this is the full function of Baruch, okay? And this is the 5x2 results. This one is Baruch, this one is the 5x2 result, so it works well, but unfortunately the time is too short to see the Z cube. So what we can conclude is that when the time grows, the Tracy-Widom distribution or the long time behavior starts from the right, conquer the bulk, and then at the very last moment will go to the left, okay? So this is what we can say with numerical simulation. But with this method, we can also study, I mean, we didn't do up to now, but we can also study all the other boundary conditions. And for example, the 5x2, the cubic, and the 3x2 are supposed to be very universal. The non-universal part is only in the prefactor. And we can also study, this we didn't do, it was a mistake, we can also study how the configuration looks like in this extreme event. So the polymer here, it will be very different from the typical polymer in the standard optimization process. So how much minutes I have now? Because I have a new, I don't know.
Okay,
So
I'm going to, so I'm the chairman.
Yes,
5 minutes, no?
5 minutes?
I don't know, we start at least 5
Yeah.
minutes.
So if you let me 10 minutes, I can finish.
Okay.
I maybe less. Okay, so now I want to, the second point is, okay, this rare, I'm happy, I was able to see these tails, which are very rare, with the probability very small. So, but are these rare events important? Because important for applications. And so this I will follow what you did, David, the first. So are extreme events important? Yes, because sometimes they are crucial. So I'm not able to find a direct application for the ground state of my direct polymer, but I can find a clear application of rare events of the first gap. So the difference between the ground state and the first excited state. This is a work with Chen Liu that is doing the postdoc with us, Andrea De Luca, who is now CNRS in Paris, and Laurent Talon, who comes in a lab of our university. And what they do is they study the rheology of the liquids in porous material. So it's motivated by that. So, what happens is that, I mean, most of the water, which is sweet water, is not on the lake, on the river, but is actually underground, okay? And is contained in sand or fractured rocks. And this became very important in the 19th century when there was the cholera, because people want to extract this water in order to have pure water and solve this problem of cholera. And the first town with public water is Dijon, and Darcy was the engineer there. And what Darcy did also, did experiments. So they put granular material like sand of clay in this column, and they put water here with some pressure P, and what they measure is how much water Q comes out in the unit of time when you fix the pressure P. And so the Darcy law, that is the law for all Newtonian liquid, is that this is linear with P over L, so the gradient of the pressure, and the coefficient of proportionality is called permeability, and it strongly depends on the material. The sand has a very good permeability, the clay has a very bad permeability. And a problem in this century, or in the last century, is to compute this value. So you have to simulate a porous material, and it's very complicated. So what people use are models which are called pore network models, okay? Network pore models, sorry. So what you assume is that this region is done by large voids, like this one, where the pressure is well defined, sorry, Pi, Pj, and then you have narrow channels, narrow throats, in which the water flows, okay? And so you write equation like the Kirchhoff equation. So this is the flow of water in this channel. It depends on the local pressure drop, and this takes account of the fact that the channels are not equal. They have some distribution, and this is the equation that you write in order to say that the water that come in is equal to the water that go out. And so these are linear systems that you can solve, and that gives you, given sigma ij, they give you pi, q, and then they give you the value of kappa, the macroscopic value of kappa. But what we did today is to consider non-Newtonian fluids. For example, when you extract petrol with these new, very non-ecological methods, you inject foams or liquids which are liquid with a threshold that become liquid above a certain threshold. And also here in Pisa, to fix the tower, they put cement, okay? And so how the cement flows in a porous structure, how cement flows in the ground. If the gradient of pressure is not large enough, is not large of a certain threshold tau, it doesn't flow, okay? So now the law becomes nonlinear because there is no flow if the jump in pressure is not high enough. And this variable tau ij is random. For simplicity, I take the other one equal to 1. And so now you have to solve this system with nonlinearities, okay? And we can do it numerically. I will not tell you how. And this is our result. So this measures the amount of cement for a given pressure P, okay? And you see that below P0, there is no flow. And then the flow starts, but is not linear anymore. So the Darcy law changed dramatically. At the beginning is linear, then you have a kind of nonlinear behavior that we try to understand, and then is linear again. And now if you make a blow up of what is happening here, this is what you find. So you find that at the beginning, the flow at P0 is linear with some permeability kappa 1, but then there is a pressure P1 above which you have a new slope. Okay, it's linear again, but with a new slope, and then a new slope again. And you can understand what is happening, because now you inject your fluid here with some pressure P0, here is with some pressure P, and here is 0, and up to P0 there is no fluid. And then when, for the value P0 at which you find a path that is able to overcome all the threshold along the path, then the cement can flow, and then you can solve the system, and this is what you find. So you find a linear behavior, and because I chosen sigma equal to 1, this is the permeability of this system, okay? But at a certain point, there is a new path that opens, okay? And this happens, if you solve the equation, when the gap between the ground state and this new state, okay, per unit length, this is the length of the reorganization. If you minimize this quantity, the gap per unit length, then you have the minimal pressure at which a new path opens. And if you solve now this system, you find a new linear behavior with a new permeability that is given by this expression. So if small l, if the reorganization is system size, kappa 2 becomes 2. So you can change of a factor 2 the permeability, okay? And then the more you increase the pressure, the more channels opens, and when all the channels are open, you go back to the standard Darcy law.
But with a different coefficient.
With a different coefficient that is log L, in this example, okay? So the coefficient change at each channel, okay? And so we were asking, what are the statistics of L? So as I said you at the beginning, when Chen came and said, okay, Chen, here the gap, when you reorganize a polymer on the size L, we know since the 80s the energy should grow like L power 1/3. So now you want to minimize this quantity, which is this energy divided by L. So because of this factor 1/L, I expect that you have reorganization that are of the system size. So kappa 2 should be 2, okay? If there was no this term, then the reorganization should be of size 1, okay? Because you want to minimize the gap. And so try to see if it works, and actually this is what he found. So I was expecting a red distribution peaked around L, and blue distribution peaked around 1, and actually found 2 power law distribution with exponent consistent with 1 and with 2. And so this is, so I was shocked at the beginning, and then I thought, and I remembered that Andrea De Luca and Pierre Ledussal made a paper where they show that there are rare samples in which you can find two ground states. They start from a point and arrive at the same point, so the gap is vanishing. And the probability of this sample goes like 1 over L. So the more they are long, the more they are rare. And so we looked with him at the distribution of the gap. So you fix the size of the reorganization. You look at the distribution of the gap. The bulk of the distribution is exactly around L power 1/3, okay? But you have a plateau here. What we can show is that this plateau goes exactly like 1 over L. And now, because I have no time, I will not explain now, but supposing that this distribution vanishes with the factor 1 over L, and using standard argument of extreme value statistics, you can show that the decay goes like 1 over L. So the channels are scale-free, these channels are scale-free, and with no characteristic size. Okay, so rare events are important because they explain how the flow of cement happens in the ground. Okay, thank you very much.
So questions?
Here. So here, the flow between these 2 points is 0 below a threshold. So and it becomes non-zero above this threshold. So generic, they can have an exponent here, okay, which is called Urscherli-Berkeley. But okay, here we use the linear response, okay?
So actually I have a question or a remark. You know that blood flow in the brain can be modeled, at least to begin with Newtonian, and then there's also a non-Newtonian fluid. The heart is pumping, is pushing the fluid inside the capillary of the brain. And then if we go back to your slide where you have all these trajectories, actually what would be interesting, I mean, if you're interested in going that direction, suppose you have now a hole in this domain which could mimic brain vascular accident. That is, some paths are not available anymore.
Okay.
And so you are interested in what would be the path, the new path that will be available. And this is very important. It has dramatic, if we could understand that, it would have important consequences. So today, for example, this network could be reconstructed, actually. Yet, the amount of paths are enormous. And yet, it would be very interesting to have an approach to be able to understand what would be the optimal path after such accident, to understand how the blood is redistributed.
So what I can say is that if you are able to make a lattice model of your possible path and so on, I mean, I didn't explain how we construct all this path, but the basic brick is still this Dijkstra algorithm. So it's a little bit sophisticated. What we do is not the simple application, but it's still polynomial to construct all this path, okay? Again, because what you have to do is not to enumerate all the paths, but they grow like the size of your system, the size of your region, okay?
Okay. Okay, so if there are no more questions, let's thank the speaker again, and let's move on to the next one.
Okay, thanks very much to the organizer for the invitation. I like a lot the conference. I will speak today of level 2.5 in large deviation. It's work that I mainly did with André Barato, which is now in Houston. Some little at the end with Hugo Touchet, with his Stellenbosch, and with Alexandra Fagionato, Gabrielli, and Bertini, which are in Roma. And first, before to enter, I will do a long introduction on large deviation. And what is large deviation? Typically, you have a random variable, a to t. T, in my talk, would be time. But in general, you can imagine number of particles. You can imagine a lot of things. And then, at large t, this random variable become not random, become a typical things, which are not a bracket. And the question of large deviation, it is, can you quantify the improbability that at t converge toward something which is different at a bracket? So in general, it is 0, because I tell you I go toward a bracket, and the large deviation tell you in general, oh, it is 0. And in a lot of cases, it is 0 with the exponentially decreasing in t form. And this function which appears is called the weight function, is positive. And what we know, it is 0 in the typical value, because in the typical value you don't want to have the decreasing. And then the large deviation theory has two ends. One mathematical end, which will be to prove that this form is true. It is wrong in a lot of cases, and so it's complicated to prove that this form is sometimes true. And the second end will be more physicist way to tell, okay, we are not happy with the fact that it exists. We are happy if we have an explicit expression for the weight function. And now, what I will do is very close to what Alberto just said, is that maybe if you don't know, if you are not really aware to large deviation, maybe for you, you can tell, okay, why large deviations are important? Why events of probability 0 can have an impact on something? Maybe it is just a hobby of mathematicians, and maybe this is important for nothing. And the main message of my, no, it's not the main message of my talk, but it's the most important message finally, but after my talk we will not speak of this. It is this sentence in red, means that the large deviations are important because the large deviation of some observable appear in the typical value of another observable. And every time that large deviation is important, it is because of this. Okay, I will prove now this sentence, but before to prove, I can tell you that it is the same in the common life. You have events which have very, very, very weak probability, but if they have big impact, and if the big impact compensates exactly the weak probability, then it will be important. There is events in the common life, as earthquake, which have very weak probability, but if they have big impact, then the ratio compensates exactly, and then it becomes important. And then, imagine, by example, that I come back with my observable a to t, which have a rate function of large deviation e to a, and then instead to look at the t, I will look at t power qt. And so you see what will happen. The fluctuation of a t is still very little. But now, when I will deviate a little from a bracket, the power qt here will do that it will be a big impact. Because now a little deviation will have a very big impact in at power qt. And it will exactly compensate. So this is an important formula, means that if I look the typical value of this new observable, which is 1 over t log of the expectation of at power qt, I will do the calculation after, then I find that this typical value, this is not at all a rare event, this is just a large time, then is given by the sup over a of q log the a minus the large deviation. So you see, large deviation in this case are given by, typical value of this are given in terms of large deviation of this observable. So the proof is very little at the physicist level, means that I begin to express what is the expectation at large t. So at power qt is exponential de qt log de a, and now the probability that I deviate is given by exponential de minus t e de a. Then I am exactly in this case where the decreasing effect for the probability, which was in exponential minus t, is compensated by the biggest impact, which is in exponential plus t. And then with saddle point, I arrive to this, which is here. So by example, one of the most beautiful for me application to large deviation is transport property in velocity field, in random velocity field. So by example, this is a continuity equation, totally normal, except for a density, for the density field, except that my velocity here is random. And this can be solved directly with Lagrangian flow, with characteristic equations. So I introduce this my Lagrangian, which follow my velocity, rt de r, and r0 de r was the initial position at time 0. And then I can solve this equation in blue with characteristic, except that here my v is inside my nabla, not outside. Then it will have just a new things. It means that the Jacobian of my transformation will appear. So nt rt is not exactly constant on the trajectory, but is compensated by this Jacobian. But I can write this Jacobian as this, n0r, expressed the minus t time 1 sur t log of the Jacobian. And in fact, this quantity which is here, 1 over t log of the Jacobian, here there is the ergodic multiplicative theorem in general, which tells you that this is the quantity which stabilizes. This is the quantity which have a typical value. This is the AT of before. And then I am here, I am exactly, in this case, what is the stabilization, what is the typical value of this AT? It is the sum of the Lyapunov exponent. And then, if I want to exactly same before, no, if I want to have this object, so the average of nt along the trajectory power alpha, then I come back exactly to this case, and for obtaining the typical value of this, I need to have the large deviations of this around the sum of the Lyapunov. The large deviation function of this will give me the typical value of this quantity. Is there a question? So this was for justify why large deviations are important. Large deviations are important because it's become, for other things, for other looking of the, or looking not for English, for other way to look the system, then it becomes typical. It appears in the typical value. So just a little, I show you these right functions. In fact, large deviation functions have a dual way with these scaled cumulative generating functions, which is defined as this, means the large time limit whenever t is the log of the expectation of the exponential of ft at t. And then there is two theorems in large deviation, which for physicists are almost evident. The first is the Varadan theorem, which tells you if I have a large deviation, if I know this, then this function is given as the Legendre transform of my weight function. So the proof for physicists is almost evident. Once again, I do explicitly the expectation, express the STA, and then I put my rare events, the probability that at t equal little a is at large t, express the minus t e de a. Then I can do the saddle point, and then I arrive to this function. And there is the reciprocal theorem, which is called Gardner-Ellis, which is a little more complicated, which is that if this exists and is differentiable, then the large deviation function exists and is also given by the dual reciprocal. But then I will need this hypothesis, which is the differentiability of the scaling cumulative generating function. And if I use this theorem, then I arrive just to strictly convex right functions. Means that a lot of points where the physics is interesting, this theorem is not good because it's precisely the fast transition is precisely when this is not differentiable. Okay. Now I will start to arrive in my talk. I tell you the large deviation have two ends. One to prove that this form exists. One to show you that you have sometimes explicit functions. And I will focus me on this analytical large deviation. And the key example for this is the Sanoff theorem for RE decays, which is called Sanoff, which was in fact the first result of large deviation, which was proved by Boltzmann, in fact, for independent particle. So it's really the first example. Here I will do in a very toy model. Imagine that I play with a coin, and I have two tails or head. Then my just two states. Probability of head is p0, probability of tails is p1. Then I look a sequence of n times where I play with this coin. And this is the trajectory then of the experiment. And then I define my empirical density, which will be the number of zero of head that I have in my trajectory divided by the length of my trajectory, and the number of one divided by the time. Then the probability was constructed such that typical behavior of this quantity at large n, this go toward p0, which was my intrinsic probability, and this go toward p1. And the untypical behavior here is very simple to calculate. It means that here we have a very easy combinatorial way. Imagine that I want that this empirical density of head is u0, with mu0 different than p0, and my empirical density of tail is mu1, with mu1 different than p1. This means that I want n mu0 head and n mu1 tail. So my probability will be p0 times n mu0, p1 times n mu1, and after I must just choose where I put the tails in my trajectory, the place for the tails. So this is a combinatorial Cn mu0 against n's. And then this is exact. Large deviation will just look what is the behavior of this at large n. So I take the log. I will use the Stirling. So the first term becomes this first. The second becomes this thing. After I use Stirling for n factorial, I use Stirling for n mu0 factorial and for n mu n factorial. And then all the things which are in pink disappear. All the things which are in black disappear. Why they disappear? Because I forgot to tell you that I choose an untypical behavior. Not so untypical, means that I choose that mu0 plus mu1 equal 1. If not, it's totally too much untypical. I choose to be different than p0, but that the sum of the two rates are 1. Then I arrive to this result, which is I think the most beautiful result of large deviation, which is that the probability, the rate function is the relative entropy between the mu distribution, which is an typical behavior, and the p distribution, which is a typical behavior. So this thing is very beautiful because it gives a links between entropy and rare events. Okay, and this is a result that we will lose in the following of my talk, and this is the result I want to come back. So this type of result. So for this, I will define a little what is level in large deviation. Typically, level 1, it is what we are interested in physics. You have some observable, A, and then you do this empirical average, and you want to understand the average, the large deviation of ATE, AT empirical. It can be the work, it can be the heat, it can be the number of particles, it can be a lot of things, number of jump. Okay. The level 2 will be the level that you just saw in this Sanoff, which will be the empirical density or the large deviation of the local time spent in a state. Means that every time that I am in X, I count 1, and I define this quantity. Okay, there is some hierarchy of level. For arrive to the level 3, I will come back to discrete time, just because it's more intuitive. So here, I count the number of times that I have the word X with one letter, but you can in my trajectory. But you can imagine to count the number of times where you have consecutively XY or consecutively XYZ with a word with many letters. And then you have all your hierarchy. For example, here it's the number of times that I have X1, X2, Xn. And you can do this until n go to infinity, which will be the level 3. Okay. Then, what is important to understand is that when you understand the higher level, in a sense, you understand the lower level. How? By the contraction principle. By example, I will show here that the level 1, if you understand the level 2, then you understand the level 1, because you have this formula, which is that because here there is a delta functions, this quantity here, which was written here, can be also expressed as a space integral of a de x against the empirical density. And then the fluctuation of A can be expressed as the fluctuation of the empirical density, but with a constraint, which is that the untypical behavior of the empirical density integrates against the A must give the untypical behavior that I want of my observable. Okay, but this I know that if I have the level 2, this behaves as the exponential de minus t I to the rho, which is the level 2, and then I arrive to this, so I can do a saddle point with constraint, and then I arrive to prove my level 1, which will be known in a variational form, means the minimizations of my function at the level 2 with a constraint, which is this constraint. So this is very good, but this we must understand that by doing this, in general, we lose the explicit character. By example, if I do this for the I decays, where I just prove that this was explicit, this was relative entropy, in general, by doing this minimization with constraint, I have no explicit things. Also for IED case, I have no explicit things for this level 1. It is loose in the minimization. I have a minimization, but in general, I'm not able to solve the Euler-Lagrange equation. Okay, so I show you now that this level 2 was explicit for IED. I show you that in general, you lose the explicit way by minimization. But IED was a very, very peculiar things. And now I will show you one step a little more realistic, which is a Markov process. And then the level 2 for Markov process was considered in a very famous theory by Donsker and Varadhan in a 4 paper between 1975 and 1982. And they prove a variational formula for the level 2, which is written here. So rho is untypical behavior of my empirical density. F is the auxiliary function, which is minimized. And L is a Markovian generator. If you don't know what is a Markovian generator, when you write the Fokker-Planck equation, the right-hand side is the adjoint of the Markovian generator of mathematicians, the formal adjoint. Okay, so you have this formula, and in general, you can just try to solve, once again, the Euler-Lagrange equation, and you will not success. You will arrive to the equation that you can't solve, except in very peculiar case. By example, if your initial process was in detail balance, so was reversible with respect to a density that I note rho equilibrium, then I can solve this Euler-Lagrange equation, and then I arrive to explicit formula, which is called a Dirichlet form for my level 2. But except this, in general, I stay with this minimization.
So this formula, formally it is explicit, but this integral usually cannot be done explicitly even for very simple models.
You speak of the first or the second?
I'm speaking about the second. You just take a simply looking process and you plug everything in, and formally it's a result, but you cannot integrate it. And you want to contract it after that, and you're stuck because you even cannot calculate this stuff. So to what extent is it useful?
Okay, this for you is also this problem?
No, this is a simple problem.
But this is an integral also. Integral of u log the u over rho. I don't see why this is more complicated than the integral of u log the u over rho. It's the same complexity. You have a space integral.
I'll show you a couple of examples.
Okay. So this was level 2, and in this series of papers of Donsker and Varadhan, there was also this level 3, which was explicit, but very, very big, because the level 3 controls the fluctuation of this around the path flow. So it's very, very big, and it's far from physics. So in a sense, it's not really what we want, but I will not speak of this. Okay, now I will come back to what I want. It means I want something where I refine my explicit things, that was loose here, but less big than this, less big than level 3. I want some intermediate level, between 2 and 3. And then we'll call this level 2.5, which formally can be defined as a less detailed level, such the large deviation functions are explicit. Typically, there is 2 methods of proof, spectral proof, which are mainly in my article with Barato. In a sense, it's the original part of the article. And I will not speak here of spectral proof because it's technical, and I would prefer to speak of something intuitive, which is a tilting proof. The bibliography, a lot of articles since long time introduce more or less or partially this level 2.5, beginning by mathematicians, Kazidis Falran, De La Fortelle, or physicists, Cherniak, Chertkov, and Christian Mass. So here I will introduce what is this level 2, what is this tilting philosophy for proof large deviation. And this is very important because in a sense, here I will use for proof this level 2.5, but it's totally general. So I will try to be totally formal and very general, just for give you the idea. So imagine that I consider a stochastic process in a class of process C. You can imagine what you want as a class, IID, Markov, semi-Markov, continuum time random walk, what do you want? Then I will look for a family of empirical observables. I will not tell you for the moment how many observables I have. So how many observables I have in this set. There is the empirical density, but it can be other observables. And my goal will be to find how many observables I must to put here, what observable I must to put for have an explicit large deviation function. So they will have two conditions, which are the roots of the method. The first conditions, and I must tell that the method is related to what Alberto just speak with this ratio of importance sampling. This will appear at the middle. But for the moment, there is two conditions. My condition one will be that it exists another process, X prime, maybe in another class of process, C prime, potentially biggest than the class C. By example, C was RID class, and C prime, by example, is Markov. Such that the behavior rho alpha, which was the untypical behavior of this for X, become typical for X prime. So I can twist my process for transform untypical in typical. You will see why I will need this. And second conditions, it exists a function that I call E2.5, but you can call, because I know my result, but it can be just a function, such that the path probability of the ratio between the X process and the X prime process at large time will depend just of the path through my empirical quantity. So in general, P de X depends of the path, P prime of X depends of all the path, and there is no reason why I can tell, okay, look, it is just a function of my empirical observable. And here I will ask this. I will ask that I choose my empirical observable in a way that when I do this ratio, it don't depend of all trajectory, it depends of trajectories just through the empirical observable. And then if I have these two conditions, my 2.5 is explicit and is given by this relative entropy in the path probability between the prime process, my tilting process, and my untilting process. And in general, you can explicit this. I will do after for jump and for diffusion process. Now I will prove this. You will see that after that I define condition 1, condition 2, it's very easy to do the proof. So I want to have this. I want to have the probability that my empirical observable are fixed to an untypical value for all the possible empirical observable. So this is defined as the path probability for each trajectory with a constraint. Now I do, as Alberto, a ratio between P and P prime. Then I multiply by P prime. And then this is just that I pass from here to expectation with respect to prime process, except that before I had just the constraint. Now I have the constraint times the ratio, which is P on P prime. But then my condition 2 was that my ratio, P on P prime, depend of X just through the empirical quantity. So this becomes this. And then as there is a delta function here, this can go out the expectation because this is fixed to the untypical value. So this becomes extra the minus T E2.5 of the untypical value. And I remain just with this expectation with respect to prime of the constraint. But I choose my hypothesis 1 such that this is a typical value of this for the prime process. So this becomes 1 in this scale. And then I finish. I finish the proof. So this is the idea of tilting. So now, wait, of course.
The ratio of probabilities for each history that realizes these are observables is independent of the trajectory.
No, it's not independent of the trajectory. Yes, yes. If you fix the observable, yeah. It's not independent of X because X appear here. Yes. All the empirical quantity depend on the trajectory.
So, I mean, it's not exact, but only in the long time limit.
Yes, only on the time limit, exactly. In the case that I will show you after, it will be exact. In the Markov process that I will show you after, it will be exact. But potentially, you don't need. You need to have just this in the long time limit, yeah. So, I come back, by example, to the RID case. And my hopes is that the level 2.5 will be the level 2, because I show you that you have Sanoff. You have the level 2, which is explicit. Then I consider just this empirical density for XC, which is ID with low mu. And then it's evident that the condition 2 is verified, because if I do ratio of path flow is product of mu for the low P, product of mu prime for the low P prime. But product and product can be expressed as the exponentials of the sum of log of mu or mu prime on one point function, xi, and then can be contract with this object. So my condition 2 is good. I can think a little and see that my condition 1 is good also. If I choose mu prime equal the untypical value that I want, so if I invent a ID process such that is low is the antiperical value. Then here I just need to change u prime in rho, and it gives me my result before. That my weight functions of level 2.5, which is here the level 2, is the relative entropy between rho and u. So I can do the same game for Markov chain. And by example, if I want to have just the empirical density, then I will see the problem which arrive, because when I write the ratio of path probability for a Markov chain, je voulais maybe... So when I write the ratio of path probability for Markov chain, here I will have M to pass Markov matrix to pass to x0, x1 until Markov matrix to pass to xn-1 to xn. I will have the same things here with M prime. So this can be put as a sum, but exponential of a sum of log of 2-point function. I will not be able I will stay with object with the point of xc on xc plus 1, and then this is not contractible with this quantity, which is here. So I must to go to just what will be able to contract will be to go to this word with 2 letters, which is the empirical density. And if I do this, then I will find with my 2 conditions the level 2.5, which will be the relative entropy, a little more complicated. Okay, then I arrive to what I want, means to do the same game for jump process for the moment and after for diffusion process. So finally you understand that for check the condition 2, I must write the ratio of path probability for jump process for the moment. And if I do this, the path probability of a jump process has 2 parts. One part which is a product of transition rate. This is every time that I jump, and one part which is a waiting time, which is the integral of the escape rate. So I must do the ratio of this with W, this with W prime, this with the escape rate lambda, this with the escape rate lambda prime. The first ratio will be contractible with this object, which count how many times in my trajectory I pass from a state to another state. The second ratio, which will be here, will be contractible with my empirical density, my normal empirical density. Then I can do this, and I will find the explicit expression for the level 2.5 of a jump process. Okay, I will jump this. We can find a first application, by example. Here, as it explicit, I can find directly a Galotti-Cohen at this level 2.5, just by checking directly. Because all is explicit, that E2.5 rho 2 adjoint minus E2.5 rho 2 will be given by this rate of entropy productions. And then, this I call this level 2.5 Galotti-Cohen, because if you contract this relation, you will find the normal Galotti-Cohen for the entropy production. I can do the same game for diffusion process. Here I introduce this Markovian generator, so it is the adjoint of which appear in the right-hand side of the Fokker-Planck equations. This object will play a role, which is the hydrodynamic current associated to the Fokker-Planck equation. So this is a convective current, this is a diffusive current. And then, once again, I must to do a ratio between P and P prime. So if you're a mathematician, you can use this Girzanov. If you're a physicist, you will write P as the Onsager-Mar loop, and we compare with the P prime. For that it has a sense, you don't need to touch the D, because if you touch the D, it will be infinite, this ratio. If you have here, so typically this will be 1 to the x dot minus drift square. Forget the multiplicative noise that is here. Here will be 2 d prime potentially x dot minus f prime square. Okay, and you see that if I begin to touch the d, the term in x dot square will not disappear. This is a catastrophe, because it has no sense also for mathematicians. So you don't need to touch the d, but you can touch the drift without problem. This is a Girzanov theorem for mathematicians. And then if you do this, you understand that the term in x square will disappear. It will stay a term in x dot f minus x dot f prime. This is perfect. And it will stay a term in f square, f prime square. So the first term is contractible with the empirical current, which is written here. And the second term, the term in square of f, will be contractible with empirical density. If I do this game with this condition 2, the condition 1 will be checked if I choose well my f prime. And then I arrive to this quadratic form, quadratic in G, for the level 2.5. Once again, I can check the Galotti Cohen symmetry. And once again, it will give me that at the level 2.5, the difference between E2.5 rho minus G minus E2.5 rho G will be given by the rate of entropy production. Okay. Is there a question for the moment? So now I will pass to more complicated things, which is this level 2.5 for time periodically forced continuum time Markov chain. So typically, you can do the same for different process, but typically it is a chain which is non-homogeneous in time, but the non-homogeneity is periodic, in the sense that the rates are the same at little t plus big T, which is a period, and at little t. This type of process are not ergodic, but in a sense, yes, they are ergodic around oscillatory steady state, which is the invariant density which depends of time, but which is periodic. And then you can look large deviation around this oscillatory steady state. So now the quantity which will be a little more complicated, this level 2.5, if you do this game of condition 1, condition 2, that we will find, it is this object, which is the number of periods where at time s of the period you are exactly in x, and this is the number of periods where at time s of the period you jump from x to y. So you can show that you have typical behavior, that this goes towards this oscillatory steady state, and this quantity goes towards oscillatory steady state times w, and this typical behavior solves this, satisfy this master equation, which is a typical behavior. And now you can find the 2.5 with the same method, which is very similar to the 2.5 that I just showed for jump process, except that there is a time integration here. Okay, I finished my talk of 2.5. Now I will tell you a little of how can I apply this. And the first application will be that now that I have something explicit for the 2.5, I tell you in general I lose the explicit way when I come back to 2 or to level 1. But okay, I will have a variational formula, and maybe I can use this variational formula. So here I write the things for diffusion process. It is more or less the same for jump process. So if I want to come back to the level 1 of large deviation for this class of observable, so which consider of a scalar field f de xt and a vector field g de xt dxt, here the convention of discretization is Ratanovich, and there is also a summation of the vectorial index. Okay, this can be contracted with the empirical object that I introduced before for diffusion. So it will be just the scalar product between the empirical density and f, and between the empirical current and the vectorial field. And then, if I want the large deviation of this object, it will just be minimization of the 2.5 level that I introduced before. Means that, by example, at the level of the rate functions, the level 1 will be the minimization of the level 2.5 with a constraint which will be here. The same for the scaling cumulant generating functions. You will arrive to a minimization without constraint. So this is dual minimization. And by example, first application, this generalizes the Rayleigh-Ritz variational formula. Because if you take g equals 0, and that you begin with, I forgot to tell, that you begin with the case where your process was reversible, then you have this explicit formula that I showed before, that Baruch tells that it's not useful. And then, no, I am commensable, no problem. It was just for that people remember the formula. And then, if you put the explicit formula of this explicit formula, then you arrive exactly to the Rayleigh-Ritz variational formula, by example. Okay, but this gives also a rationalization of something which exists in science or also in physics in very long time, which has this maximum caliber method, where finally, for justify no equilibrium, where finally people begin with this type of functional without no, by telling in an ad hoc way, but it was the level 2.5 without no. And when they do the extremization for find the new dynamics with constraints, finally, they do exactly this, just they don't know that they begin with 2.5 and they arrive at 1, because they do in an ad hoc way, but it was this. Okay. We can also, okay, here the minimization was in rho G. We can also restrict the minimization, by example, on drift. And then you arrive to variational formula for this level 1, which are useful for numerical formula, by example. But okay, I think it's too technical. Okay, the application 2 that I want to show you is this quadratic bound of level 1 that I will find from the level 2.5 once again. And from this, I will prove, it's not me who will prove, but in this case, they prove the uncertainty relation, the thermodynamic uncertainty relation. So this was mainly in 2 articles, Barato-Seifert, this was the uncertainty relation but without proof, and Gingrich, Horowitz, Perunov, England, which was a proof of the uncertainty relation with the quadratic bound that I will show you here. They do this for jump process, and here I will show you for diffusion process. So once again, I consider this class of observable. You can show very easily that this is a typical behavior that I note A bracket A star, which is just the scalar product between the invariant density and the function f, and the invariant and the scalar product between the current, the Fokker-Planck current associated with the invariant density and the function g. And I will introduce an object which is called the rate of entropy production. This is another story, but it's very famous since 20 years, which is this scalar product between, once again, this g and g, but with a metric which is given by this the covariance matrix of the diffusion process. And then, what is this quadratic bound? It is the fact that, thanks to this formula, which was here, I can choose in a suboptimal way rho star and g star, which are not optimal, but in a way that this gives me that I obtain a quadratic bound here for all level 1 function, which is in a sense universal, not totally universal, but because there is this sigma which appears for all possible of observable. Here it's quadratic, A minus A star. A star was a typical behavior. And here there is something which is also A star in the case which was considered historically, where there is no F. Because in general, people don't know what I show you here. They consider, without Feynman-Katz term, the observable, so just this G. So here at this moment, here, this is also A star square. And after that I have this, you can tell me, okay, this is useful for what? But this is useful for prove this uncertainty relation, because you see that this is a quadratic bound. Moreover, this was 0 in A star. This is 0 in A star. So the first derivative of in A star was 0. The first derivative in 0 of the right-hand side. The first derivative of A star, no, the first derivative of the right-hand side in A star is also 0. Then, if I have this inequality, the second derivative is also true. The second derivative is also a bound. And if I do this, and that I define the diffusion coefficients of the observable at t just as the variance at large t, with this directly, I arrive to this bound, which is that this diffusion coefficient times the rate of entropy productions is bound by this, which when f equals 0, this is just A star square, so it is just the typical value square. So you can rewrite this with a Fano factor if you want, but at the end, this tells you that if you want to localize sufficiently an observable at t, so if you want to diminish the dA, you have a problem that sigma become big. It's for this that they call this uncertainty relation, because so there is this relation between the fact that if you want to have observable with very little variance, you must have big dissipation. The dissipation is measured in terms of this relative entropy. Okay, so this was a very successful story, which was not did by me. And after the question directly appeared, because they want to apply this to motor. And in motor, you have not a time homogeneous Markov process. You have in general a time periodic Markov process. And so there was a question which was, what becomes this in the case of time periodic process? But here you see that the level 2.5 is very important. I don't show, but in the proof. This can be proved if you begin with 2.5. And the level 2.5, finally, I proved this for time periodic process. I proved this recently, 1 year ago. Then we prove this level 2.5 that I showed you before, and after we apply improved proof, I will tell a little more complicated proof, and the result of the proof, you can forget all, just there is a kind of uncertainty relation, more or less the same, except that it is not the sigma, it is not the rate of entropy production which will appear, it's a quantity close to this. So this bar here is a time average on a period, and you see that here you have this quantity, otherwise the true entropy productions for time periodic process will be a quantity which is little different, which will be 1/2 sum x, y, g rho 1 the xy. This is the current on a length xy associated to the invariant density. ln, the log is the same, rho 1 w and rho 1 w in the other sense, and average here. So you see that the difference here, that I have my ratio here, and my average is here, my time average is here, and so this don't become to this. And finally, you can see this in a pessimist way by telling, okay, the uncertainty relation becomes wrong for sigma, it's true. Or you can see this in an optimist way by telling that this, for me, this result shows that entropy production is just one way to look dissipation when you are out of equilibrium. And by example, here this shows that if you want to constrain the variance, you need another observable that's the entropy production, which is here, which is more complicated if your process is not time homogeneous in time. Okay, I finished my talk. For me, it's still important question to apply this type of things for quantum open systems, quantum trajectory. And since long time I tell this, but I did nothing. And I thank you to listen to me.
Questions? No, yeah.
For the time
yes.
periodic case, you also have a statement?
Yes, we have at this time we have 3 Galotti-Cohen because there is many ways to reverse the dynamic. So I will tell that it's more a duality between one dynamic and another which is related to the reversal. The true Galotti-Cohen is a symmetry between the large deviation function of the same dynamics. And in this case, you have a duality relation between large deviation of entropy for one dynamic and large deviation of entropy for a dual dynamic, which is, by example, just the rate read backward, just, for example. So we explicit three different Galotti-Cohen possible in a way where or you define the entropy or you define the reversal. 2.5. Sorry? 2.5. 2.5 is universal in a sense. Just one.
Large deviation function, you use this auxiliary process which realizes the atypical value.
Yes.
So how is this process related to the distribution of the conditioning process?
It's very related, yes. It's not so simple to see, but it's very related in a sense. In a sense, this tilting process, okay, first, tilting is not a good name because it don't correspond to tilting in my article on conditioning, you're true. They are related, but not so in simple way. So you must read this in my third article with Touchet, which was this variational and control representation. Here you see, oh, it is related. It is not so simple. In a sense, this is a exact choice of minimization. It is not, in general, you don't do this. But at the end, I use this suboptimal choice for finding the quadratic things. This was just useful for proof my level 2.5. But if you want really to do numerical simulation, I don't think it's useful to obtain this twisting or tilting. It's too complicated.
Okay, so yeah, you want to ask one more question?
Are you aware that there is much progress in this area?
Sorry?
Are you aware of the large progress that have been made in this area over the last 40, 50 years? On large deviation for quantum open systems since Feynman?
No, me, I am not really aware. You are aware?
Yes, I am aware, yes. I actually talked a little bit about it in my previous talk, but of course it's not just my work. There is a whole area of science which is called quantum optics, for example, which deals exactly with these problems.
I don't think so. I think partially.
Okay, well, trust me, there is this area of science. I don't know how much of it you know, but if you...
I know very little. But
very little.
No, but me, I speak of large Json at large time. So I speak of large Json around the typical, around ergodicity. I think you speak of large Json at weak noise.
Say it again, please.
I think you are concerned with large deviation at weak noise.
Large deviations where you have h bar, which is small, and you have large deviation from the average behavior. And this is what is of interest in quantum optics in particular, where people have been studying the tails of the distribution of photocurrent, for example, since the 60s, and so on and so forth. So it's a very, very, very big area.
Yeah, I'm very happy. Okay, maybe my sentence was not good. I wanted to really speak of open quantum systems.
And these are open systems.
Okay, very good.
Okay, let's thank the speaker again for this afternoon. Thank you.
So thank you so much. Okay, let me start. This is essentially our first work about resetting, and we have here the important authors whom we follow, and we decided to develop a heavy alternative machinery, especially when the process which you do reset partly keeps the memory. And at the beginning, I was very reluctant to look at the first passage properties, because I thought in order to get the first passage properties, you need to put boundary conditions. It might be complicated. Let's look at the PDFs. Let's look at non-stationary. Let's look at non-Markovian, and so on. But then, suddenly, we understood that for the standard case, this heavy machinery reduced to something which is so simple and so transparent that I am really ashamed to bother you with a collection of trivialities. And now I will show you really a collection of trivialities. It's a single work. It's relatively light and simple work, and I was really happy to have this feeling, you know, when something goes smoothly, when we understood how the theory works, everything went so smoothly from the very beginning up to the very end. And I must tell you also that it's my first PRL which was immediately accepted. It never happened to me before. So now let me start, and we were motivated, essentially we were motivated by the idea to build a heavy machinery, but our motivation to look at the search came from the work of Arnab, who is here, yes, and Shlomi Roiveni, whom I know since he was a student, about this first passage and the recept, and I would like simply to read the first sentence of the abstract. First passage under reset has recently emerged as a conceptual framework suitable for the description of a wide range of phenomena, but the endless variety of ways in which restart mechanism and the first passage process mix and match hinder the identification of unifying principles and general truth. It's a very nice work, written in a very bombastic manner. After you read something so bombastic, I feel even more ashamed to show my collection of trivialities. And here they had figure 1. Here they have a picture when might this search under resetting apply. Top bad weather could force a team of searchers to temporarily cease their efforts and return to base. By the time search is renewed, the target must have relocated and search might start from scratch. Second is a greedy computer algorithm which doesn't find anything, it's better to restart. Anyhow, it's better to switch off the computer and then to switch it on again. And here you have a problem of, you can look at it like a problem of DNA transcription, at a problem of protein folding in some cases, but mostly in DNA transcription. This is indeed what is done. You don't find anything, you detach, I mean, the transcription factor detaches and attaches again in a new place. So it's a random search under resetting. So now let me introduce some terminology which I will use. It might be non-standard, but I don't know how things are really called, because I'm relatively new to the field. So we have a combination of two random processes. One is a resetting process. This is a point process on a non-negative line. So this gives us simply the times at which another process, which I will call the transport process, and here I will only consider the first passage processes, properties of this transport process, is reset to the origin, to some point. In this talk, I will only consider the full resetting. So each copy after resetting is a statistical copy of the same process. The epoch between two resetting events will be called a run, and an unsuccessive run, an idle run, leads to nothing and is reset, and by resetting event. And then at the end of the whole process, there is a successful run in which a searcher finds a target. And this whole process is essentially a renewal process. You can relax in heavy machinery the renewal process property. Which you cannot relax in any kind of such machinery is the independence of resetting process from the transport one. We will consider also the case when several targets are present, and we assume that hitting of any of them terminates the whole process. Now, let me introduce some notation, because I will need quite a few different functions. And then I will combine them in different ways, and suddenly everything comes out very smoothly. So the resetting process by itself will be considered as a renewal process with a waiting time density psi of t. Here, capital psi of t is the survival probability in resetting, and I will assume that this density, or the corresponding probability, this integral, is a proper probability. It integrates to unity. At some time, you will always reset. So resetting is present. Then I have a search process, and I will denote by phi I the hitting time probability density function for target I in a single uninterrupted run. So I forget about resetting and simply looking at what happens when I start at time 0 at 0 and continuously search. Then I will need the corresponding cumulative distribution functions. For some cases, for some proofs, I will assume that this is continuous. I will need the total hitting time PDF, which is a sum. If you have several targets, it's the sum over all targets, the corresponding cumulative distribution function, and the total survival probability. The survival probability may be non-proper. It might happen that having started, you will never find a target. You get lost, and you have to wait forever. Now, what does it mean, assumed continuous?
Why do you call it total hitting time? It's not the hitting time condition that the other guys did not hit before you?
So why?
How is it normalized, the total hitting time?
Where do you see the total hitting time? It's a total hitting time PDF. It's a probability density function, which might be proper, which means normalized to unity, or which might be improper, which means normalized to something between 0 and unity, smaller than.
Assume that phi i's individual ones are normalized.
The sum of them is normalized. if you have several targets, it's about hitting one of them. It's either. Correct. Either is normalized. Each of them doesn't have to, but also either doesn't have to be normalized because a searcher can get lost. And then you restart. And this is the non-proper case. So, I'm sorry. I will need continuity in some cases, but essentially, if you think about what does it mean that this guy is discontinuous, it simply means that phi has an atom somewhere, a delta. And if it has a delta, the integral of this has a finite jump. And the only thing which changes is that you have to carefully compare the left and the right limits. And this is the only complication. I will simply not speak about this. It doesn't change too much, but one has to keep in mind that there is such a possibility. And then I introduce the mean heating time in a single run. When it exists, it is the mean value of this phi, but essentially you can express it simply as a time integral over the corresponding cumulative distribution function. And now let's have a look at a process and look at successful runs. First, it might be the first run which is successful. So you don't reset up to the time t, and you have found. You hit. The first run might be idle, and then you might find in the second run. The first run is terminated at t prime, and the second run is not finished until you find. And then the third run, and so on. And all such events in the statistical or probabilistic sense that you hit in the first run, second run, third run are mutually exclusive, and therefore you simply sum up the probability densities. Now, if you look a little bit more careful at this structure, and this is the structure, you recognize that the whole structure is built of only two building blocks, which are the products of one cumulative and distribution function and one probability density. So I will denote them by kappa I. This is the probability that there was no resetting up to time t times the density to find at t. And R of t is the probability not to find until time t and to have a resetting at time t. And if you put these as a sum of these two building blocks, not as a sum, but as if you express it in terms of these two building blocks, this is what you get. You have a structure of multiple convolutions of only two functions, where you always have R, K. So this is the structure if you put the convolutions formally as a star, and it is an extremely simple structure. Now, essentially, now about heavy machinery, but I will not go into the details, these kappas can be more complex and they can keep memory about the previous. But what you need, that R's are really independent and convoluted. Then you can do something similar but more heavy. Okay, so now in this simple case, when you fully forget what was before, you indeed have a structure of convolution. And when you see something like this on the non-negative half-axis, you come to the Laplace domain and you easily sum up the series. And this is our main expression, which I then will massage by writing explicitly the stuff and performing infinitely many partial integrations to put it then in the form I can either evaluate or investigate. Now, if I look at this guy at s equal to 0, this is simply the total probability, or the total probability to find a target I. So this is pi I, this guy here, and this is the splitting probability. this gives me how probable is that at the end, when I finish my process, I find target 1, 2, 3, 4, if there are several. If there is only one, then it's even simpler. And all further results follow essentially from the investigation of either this or this. Now, I put it there. It's very simple to come from here to here, and then I will make another transformation. I will not show it, and then I come to standard result, which you find in books, which is exactly the same. And in order to come here, from here to here, you simply have to perform the partial integration here, and to note that this term vanishes because there is no target at the origin. Otherwise, the process will never start. And a resetting event takes place with unit probability, so that the survival probability at infinity is 0. And this was my additional condition. I said that at some time you really reset. Now, if I look at these guys, I see that the survival probability, which is equal 1 minus the sum of the cumulative functions, guarantees the normalization so that the sum over all pi's is always unity, except for the case when this integral is 0, which means except for the case when psi of t and phi I are orthogonal on 0 infinity, on the non-negative half-line. So this means, and if you look at these two functions, these are two non-negative functions. They can be orthogonal only if they never deviate from 0 simultaneously. So it means that you can never find during a resetting epoch. So whenever you have a possibility to find, if hitting in a single run is possible at all, hitting on a resetting takes place with probability unity, which means you try enough time, at the end you will find, independently on how low the probability to find is in a single run. Now, let's, before we calculate the moments, and here I will show only the calculation of the first moment, but the calculation of the second moment and the rest is hardly more complicated. Before we calculate the moments, let us put the question, how many moments does the hitting probability density or hitting probability under resetting have? How many finite moments? Because, for example, it's interesting whether it has a mean, under which conditions it has a mean, whether it has a variance, finite variance, I mean. Before you calculate, it's better to know that the object exists. So again, we have our equation, main equation in the Laplace domain, and we know that this Laplace transform of the probability density is the moment generation function, moment generating function. And if the guy has n finite moments, you have in its Taylor expansion, which gives you the moments, because it's a moment generation function, n regular terms, and the next term is singular at 0. There are two situations. Simple situation when you can say what kind of singularity does it have, and then you can get essentially the exact number of moments. And the case when you don't know what kind of singularity this is, and then you can get the lower bound of the number of moments. This is a simple, you put it as a simple geometric series. You know that the function 1 over f of s has the same number of regular Taylor expansion terms as the function f of s, provided f of 0 is not 0, so provided you can expand the geometric series. And then the question is only, the problem is only to count the number of regular expansion terms of this kappa and r. And the simple case, the simplest case here is the case of the proper probability densities of hitting. with power law asymptotics. Or essentially, if this phi of t is a regularly varying function, a product of power law with a slowly varying function. Because in this case, you essentially know what happens. You can put down the expansion. So, and if this guy behaves as L to the power of t to the power of minus gamma, where L is a slowly varying function, for example, a constant, a logarithm, a power of a logarithm, the whole expansion looks like this. And in this case, this will be L of 1 divided by S. And the number of regular terms is essentially the integer part of this power gamma. So to see this, you simply perform repeated integrations and lower the powers until you can use the Tauberian theorem, which works for gamma between 0 and 1. Here I again introduce some non-standard word because I don't know how to call it. In probability theory, these integrals with non-negative function are the moments. If this is a PDF, then this is a moment. But I will use them for arbitrary non-negative functions, which don't necessarily integrate to unity. And I will call these integrals the moment integrals. So they're simply the formal constructs. The moment integrals for this guy, or for P of t, are the moments, which I'm looking for. Now, if we have these power laws, these are essentially the products, and they have the same power. So what you get is this guy times, again, in principle, some slowly varying function. And you know how many moments the thing has. And you understand that the number of moments of heating time PDF is either equal to the overall number of moments of the waiting time and heating time distributions together, or by one larger. And you can say why, when. For the non-proper case, R of t always possesses n plus 1 moment integrals. It possesses exactly the same number of moments as the resetting time. Because if you don't find in something you have there, I didn't put down the equations, you have a rest term which essentially spoils the whole expansion. So one guy can possesses always so many, and another one again possesses alpha plus beta. And essentially it's a special case of the previous situation. In this case, the number of moments of heating time PDF is not less than the number of moments of the waiting time distribution. And this is a special case of the previous situation. You simply say that a non-proper distribution does not possess any moment, including the 0th one, because it's not properly normalized. Then you can consider a more general situation where you don't know what this is. And there you indeed need to go into relatively fine integrability theorems, which I never knew, in order to estimate the number of finite moment integrals. And you see that under relatively mild regularity conditions on the products of psi of t, t to the power of n, at infinity, you again get n plus m moments. What the regularity conditions are is the following. One of them, it doesn't matter which one, has to be bounded, and another one has to be of finite variation. So this means the following. This is true provided at least one of them does not oscillate wildly. That the convergence of the moments is not due to wild oscillations at infinity, but is due to decay at infinity. But physically, typically, whatever you do with the first passage times, the probabilities decay relatively monotonically at infinity, so that the conditions are essentially fulfilled in all physical problems. So for example, if one of them will behave like a Weierstrass function, it wouldn't hold. But we have never seen such cases. So we have n plus m moments. Now let's look at the mean first passage time, which always exists when either the heating time distribution in a single run or the resetting distribution or both have the first moment. And here I look at the probability of having, of not finding, massage it in a Laplace, and introduce a new function, this x of s. I simply sum up the series. And then noting that this guy is essentially the integral of this p of s, I get an expression of the mean waiting time, tau, in terms of this function x at 0 and r in 0 in the Laplace space. Now I look at this guy and look at it in the time domain, because this is nothing else as the time integral of this x of t. And this is the expression of my x of t. Look, this is the guy. And then I perform in one of the integrals, integration by parts, and this is what I get. It's an extremely simple construct. It's the product of two survival probabilities. And when you put it like this, then it's clear what it is, because you again can a little bit massage this expression. You perform a partial integration here and rewrite first the numerator, introducing a new function like this, and then you introduce again a new function, which is this lambda divided by f of t. What is the reason? I have here a clear structure of the weighted average. So this tau is a weighted average of g of t with two probabilities, essentially with a probability and probability density. Then,
can you say what the
yes,
physical interpretation of f and g are?
once again, of f and g. F is the cumulative distribution function of resetting. Yes, and g is essentially a new function. It's a very formal construct. I don't know what the physical interpretation is, but it's the main instrument which I will use. Because with the help of g, this mean waiting time is put in a form of a weighted average.
If I look,
Yes.
g multiplied by f
Yes.
is an f that cancels.
G multiplied by f, f is cancelled. And therefore I divided this lambda by f in order to have it not cancelled. You will see the trick. The trick works. First, before I show you how the trick works, I tell you that this is exactly this. And this is a formula you can find in books. But after putting in this form and then in this form, you can do something more. Now look. This guy is non-negative and essentially integrable. This guy is non-negative and integrable. And here, provided g of t is continuous, and g of t is this, and it can only be discontinuous when this thing is discontinuous, because an integral of this will be then continuous, even then. This can only have finite jumps, and it can have finite jumps when the heating probability has an atom, a delta. So if the heating probability density doesn't have deltas, then you can use the mean value theorem, and you see that this tau is the value of g at some intermediate time between 0 and infinity, at some time. And then you get an estimate that tau is always larger than the global minimum of this g of t. And then you think a little bit and you understand that this estimate is optimal. And optimal means that the equality can be reached. When do you reach the equality? When this guy is a delta at t star, at the global minimum. And this guy is a delta when psi of t is a delta, when you reset at a constant pace. So by this you prove that if resetting helps at all, the best strategy is resetting at a constant pace. Now, if you have the delta atoms, you have to consider the asymptotics at two sides and have a look what happens there. But let's assume everything is continuous. So resetting at a constant pace is the best resetting procedure to minimize the mean search time if resetting helps at all. Now, let us try to answer the question, when does resetting help at all? Are there situations when it doesn't help? First, yeah.
Does this optimal solution unique?
It depends on the minima. Because if you have many equal minima, the solution will not be unique. But typically, again, when you consider something which has physical background, it is unique. Now, let's try to answer the question, what kinds of situations can lead to resetting which could harm? And here, again, assuming continuity, we see that it can only be the case if the global minimum of this auxiliary function g is reached at infinity, which means that you approach the asymptotic of g at infinity, which always exists, from above. It has negative derivative. It goes to infinity with negative derivative. And then you know that in the proper cases, in improper cases, resetting always helps. And in proper cases, f of t at infinity tends to unity, and this guy tends to the mean resetting time, provided this exists. You put down the equation and look at the borderline solution, and it's an exponential. So no resetting can be a better strategy only if without resetting, the probability of not finding a target decays in time exponentially or faster. In all other cases, you can optimize resetting in such a way that it will help. And exponential is indeed borderline, because in the exponential case, it simply doesn't matter whether you reset or not. It's a Poisson process. Now, if we look at this function and go into the deep non-proper cases, when f of t at infinity is smaller than unity, which means this guy at infinity is much smaller than t, you can simply neglect this guy, and you get a simple approximation. And then this is what gives you the optimal resetting time. We thought, or one may think, that it works only in the very non-proper situation, if the probability to find in a single run is very low. But essentially, it's an almost homogeneously well-working approximation. And to look at this, look at the hitting a ball from the outside, starting at position x from the center, where you have the explicit solution, when you can evaluate all the integrals. And then what you get, the approximate solutions are then like this. You can evaluate everything exactly, and these are the colored line. You can use your approximation, and these are the dashed line. This is simply the asymptotics, is not very interesting. And the approximation works until you start approximately at the half of the radius, within the accuracy of 10%. So it's astonishingly good. It's an asymptotic approximation, but works starting from something which is large when this is essentially small. You can also manipulate splitting probabilities by resetting. And here you have this construct. And after we have seen how to use the mean value theorem, it's clear what we do. We introduce a function like this, and then these are the PIs are the weighted averages of these gammas. And the PIs then lay between minimum and maximum of the corresponding functions, which depend only on the cumulative distribution functions for resetting process alone. And then you can manipulate it. And then it's nice, again, as a simple example, it's nice to look, for example, at what happens if you look at splitting probabilities on the interval with absorbing boundaries, where you start at x0 and there is a velocity, there is a drift. There is a drift moving you to the right boundary and from the left one. Since you know again the exact solution, you can get the heating time PDF, you can calculate everything explicitly, and this is what you get. So these are the bounds. And here you see that the probability to find the upstream, the upstream end tends to 1 if you reset at a high pace. This is clear because diffusion always wins at high paces, at short times. And there is a probability. This is an artifact. It's somehow an artifact of diffusion, but since the diffusion wins, and by resetting very often, you prevent the particle to come here, which is less probable, you can manipulate it from unity up to the lower bound, and of course they are summed up to unity, and therefore by resetting very fast, very often, you can prevent particle of reaching the downstream boundary, but then this probability tends to another constant. So this is essentially, and I think I'm on time, I'm more than on time, the end of my collection of trivialities up to now. So let me summarize the findings. And the summary is very simple. If heating in a single run is possible at all, heating under resetting takes place with probability unity. The number of the moments of heating time is not under resetting, is not less than the overall number of moments of the waiting time and heating time distribution in a single run together. In non-proper case, this heating time distribution of under resetting has as many moments or by 1 more than the waiting time distribution. And it's a special case of the previous. Resetting at a constant pace is the best resetting procedure to minimize the mean search time if resetting helps at all. No resetting can be a better strategy only if without resetting the probability of not finding a target decays in time exponentially or faster. And if several targets are present, resetting allows for manipulating probabilities of finding each of them, however, within some bounds, and you can explicitly find the bounds if the heating probabilities in single run are known. Of course, this is only the first approximation, and you can go further. You can make more complicated machinery, which works if the memory is not really erased. But it's really astonishing how simple the things were or are. So thank you for your attention.
Thank you very much. Questions, please.
Have you tried to look not only in one dimension, but in higher dimensions?
But look, it's not in one dimension. It's simply, you know, playing with the stuff we wanted, the problems which have explicit solution, because you have to evaluate integrals. Yes, because for example, this is in 3 dimensions.
So what I meant is that, for example,
yes,
many years ago we looked at something a bit similar, that you have a cylinder, you have little holes on the surface of the cylinder, and you ask, what's the probability to hit, you know, for example, the hole before you reach the top.
yes,
We didn't go into this possibility of modulating this resetting. We just look at when the particle is absorbed, we just put it down.
yes,
But now, according to how, for example, the hole could be distributed, we could imagine that there is a some subtlety into this resetting. This is what I meant. Going to that direction might be.
It might be interesting,
yeah.
but again, as long as resetting is independent on searching procedure, you can use this machinery. It works. So this is the crucial thing, the independence on resetting procedure, whether of simple machinery or complicated, but this is what you can not give up in all these approaches.
You said that the best strategy
Is a delta peak.
Can you say on what value this delta peak?
Sure, I can say. Because look, you have here an explicit function. This is my g. And the delta peak has to be at a global minimum of this g of t. Global minimum. And this is built of the cumulative distribution function of finding, of total, so to say, finding a target in a single uninterrupted run. And then all the rest, our toy examples were simply the examples when you can explicitly calculate this f of t.
More questions?
Is there a possibility to extend this to non-independent?
Yes. There is a possibility to extend this to non-independent runs. The machinery gets heavy and you need approximations. But you can, this is what we are working on now, so to say, continuously. What else, and what I have forgotten was that when I remembered that it's about extreme events, it's also not complicated to consider n searches, because then you simply have an extreme value statistics. The one who who finds first, finds, period, the process is finished. And the interesting question there, which however I was not able to answer during the last 2 days, because the integrals there are nasty, which you have to estimate, is what is better, to reset them all at the same times or to let them be reset by independent processes? Because you have two extreme value statistics. If they are reset at the same time, then you simply take the extreme value distribution for in F. If they are done as independently, you calculate it for each of them and then take the extreme value distribution. And you have to compare. But it's not easy. I mean, it's not trivial. I didn't succeed in 2 days, but this means it probably needs a week.
This problem, I mean, with daily independent searches, that actually originally in our PRN paper we addressed this problem.
Mm-hmm.
It is already there.
Okay. But I did know this. I simply decided, but because here you have a nice method and essentially about comparison of two integral expressions. Yes, it's easy because it's exactly the extreme value statistics.
It has interesting behavior. It has a typical versus atypical fluctuations.
Yes. This is what I wanted to look at within the scheme, but it's not as trivial as it seemed to me at the beginning.